A world where diamonds rain from the sky, where one day lasts longer than a year, and where unseen forces sculpt the cosmos. This is not a fairy tale. This is our reality. The universe is full of magical things, patiently waiting for our wits to grow sharper. It is a place where the extraordinary is ordinary, and every discovery opens a door to a new mystery. In this journey, we will explore the amazing celestial wonders far beyond our Earth's atmosphere. From our own backyard to the farthest reaches of space. Let's travel to the familiar faces of our moon, the dazzling rings of Saturn, the fiery birth of stars, and the majestic swirl of galaxies. More than a collection of beautiful stars and planets, we belong to something greater than ourselves. This journey is a reminder of how small our problems are in the big picture, and yet how significant we are in our ability to understand and appreciate the universe. So, are you ready for this adventure? From the tiny atoms that make up everything to the colossal clusters of galaxies, each step will reveal a new aspect of the universe. It's a journey of discovery, wonder, and awe. A journey through the universe. The story of how it all began starts with the subatomic particles, the fundamental building blocks of matter. In its first moments, the universe was very hot and busy, creating tiny bits of matter that would later become the building blocks of everything we see. These bits, called quarks, electrons, and photons, were the seed from which everything else sprouted. As the universe expanded and cooled, these particles stuck together to make protons and neutrons, eventually leading to the creation of hydrogen atoms. This process, marked by the release of the cosmic microwave background radiation, is a faint yet special echo from the universe's infancy, detectable even today. Now that the universe has atoms, the leap from these atomic particles to larger cosmic structures is a tale of gravitational attraction and mysterious dark matter. Initially, slight overdensities in the early universe, potentially caused by quantum fluctuations, began to attract more matter due to gravity. Over billions of years, these areas of higher density grew into the galaxies and galaxy clusters we observe now. Intriguingly, the majority of the mass responsible for this growth is thought to be dark matter, an unseen substance that does not emit light or energy yet exerts a gravitational pull on visible matter. The universe was not done growing and changing. As galaxies formed, there was a dance of evolution and interaction. Some galaxies, like spirals, grew through the gradual accumulation of gas and stars. Others, especially elliptical galaxies, are often the result of galactic mergers, showcasing the dynamic and ever-changing nature of the universe. The large-scale structure of the universe, comprising galaxy clusters and superclusters, further highlights this complexity. These enormous structures, often containing hundreds or thousands of galaxies, are interconnected by thin strands of dark matter, creating a cosmic web that spans the entirety of the observable universe. The answer to how our universe went from tiny bits of matter to huge structures of galaxies is answered by a theory called embryonic inflation theory. It offers a compelling link between the quantum scale and the large-scale structure of the universe. This theory says that the universe had a very fast growth spurt right after the Big Bang, and that this growth was influenced by small changes in the amount of matter in different places. These changes, called quantum fluctuations, were like tiny ripples that became big waves. This theory means that the universe's large-scale features are the result of small-scale events. To understand how big the universe is, let's try an analogy. If our galaxy, the Milky Way, were shrunk down to the size of a coffee cup, the whole observable universe would be as big as the Earth. That's a huge difference, right? It shows how small our galaxy is compared to the rest of the universe. And it shows how big the universe is. So big that it includes everything from the smallest bits of matter to the largest groups of galaxies, all connected and part of the same story. The Big Bang Theory is the extraordinary event that marks the inception of the universe as we know it. an explosion of space itself, from an infinitely dense and hot state. The Big Bang Theory describes how the universe expanded from a very high density and high temperature state. According to recent findings, the first microsecond after the Big Bang was crucial. As we discussed previously, during this time, the universe was filled with quark-gluon plasma, QGP, a state of matter where quarks and gluons, the fundamental building blocks of protons and neutrons, were not bound together. As the universe expanded, this plasma cooled down, allowing quarks and gluons to combine into the particles that make up the matter we see today. Researchers continue to refine our understanding of the Big Bang using advanced particle physics experiments and astronomical observations. One big discovery that supports the Big Bang Theory is the lambda cold dark matter (LCDM) model, which tells us how the universe grew and changed over time, and how dark matter and dark energy played a role in that. The CMB is the afterglow of the Big Bang, the residual thermal radiation left over from the time when the universe became cool enough for atoms to form and photons to travel freely. This cosmic relic provides a snapshot of the universe when it was just 380,000 years old, offering invaluable information about its early conditions and subsequent evolution. Another big discovery that supports the Big Bang Theory is the cosmic microwave background radiation, CMB. Arno Penzias and Robert Wilson first observed this in 1965, a breakthrough that earned them the Nobel Prize. This cosmic microwave background, still detectable today, is a faint glow from the universe's infancy, offering insights into its earliest moments and the formation of galaxies. The CMB is a snapshot of the early universe, revealing its temperature, density, and composition at that time. Scientists are trying to figure out these cosmic puzzles by studying the oldest light in the universe and by doing clever experiments and observations. By measuring the tiny fluctuations in the CMB across the sky, scientists can infer the initial conditions and parameters of the universe, such as its curvature, age, and matter content. While the Big Bang Theory is widely accepted, it is not the only way to think about how the universe started. These include the steady-state theory, which proposes that the universe is eternal and unchanging, and the ekpyrotic model, which suggests a cyclic universe that undergoes periodic expansions and contractions. Additionally, the string theory says that our universe is just one of many possible universes with different rules. Each of these theories attempts to address certain aspects of the universe's origin and evolution that the Big Bang Theory does not fully explain. But the Big Bang Theory is still the most convincing and well-supported model because it has a lot of evidence and logic behind it. As scientists keep researching, we will learn more about how the universe began and what it means for us. From the smallest subatomic particles to the largest clusters of galaxies, everything is connected by the laws of physics and the history of the cosmos. The cosmic journey from micro to macro reveals the beauty and diversity of the universe, as well as the challenges and mysteries that remain. Our universe is home to an astonishing variety of galaxies, each with its own unique characteristics and evolutionary path. The life cycles of stars within these galaxies contribute to their richness and diversity. Understanding these galactic wonders offers insights into the very essence of our universe. Spiral galaxies, such as our Milky Way, are characterized by their flat, disc-like shape with spiraling arms winding out from a central bulge. The arms of a spiral galaxy are often sites of intense star formation and are populated by young, hot stars that give these arms their distinct blue hue. The central bulge, in contrast, typically contains older stars. A variation of spiral galaxies is the barred spiral galaxy, like NGC 1300, where a bar-shaped structure of stars runs through the galaxy's center, with the spiral arms extending from the ends of the bar. Our galaxy, the Milky Way, is a barred spiral galaxy containing hundreds of billions of stars. It features a distinct spiral structure with a central bar and a bulging core. Our solar system is located in one of its spiral arms, about 27,000 light-years from the galactic center. The center of the Milky Way harbors a supermassive black hole known as Sagittarius A star. Elliptical galaxies range from nearly circular to highly elongated shapes. They lack the distinct spiral arms of spiral galaxies and generally contain older, redder stars with less gas and dust, indicative of less active star formation. An example of an elliptical galaxy is M87, also known as Virgo A. The intensity of light in elliptical galaxies decreases smoothly and monotonically from the center, and they often harbor supermassive black holes at their cores. And then there's irregular galaxies. These galaxies do not fit into the spiral or elliptical categories. Their appearance is typically chaotic, without a central bulge or spiral arms. Irregular galaxies, like the Large Magellanic Cloud, are often rich in gas and dust, hosting regions of active star formation. They are thought to be shaped by gravitational interactions or collisions with other galaxies. Moving on, let's explore the life cycle of stars. The life of a star begins in a nebula, a giant cloud of gas and dust. Under the influence of gravity, parts of the nebula collapse and form protostars. These protostars eventually become main-sequence stars like our Sun. The life cycle of a star depends significantly on its mass. Massive stars end their lives in spectacular supernovae, exploding and releasing their elements into space. This process often leads to the creation of neutron stars or black holes. Neutron stars are incredibly dense, with the mass of the Sun compressed into a city-sized sphere, while black holes are regions of space-time exhibiting gravitational pull so strong that nothing, not even light, can escape them. The universe is full of exotic phenomena that challenge our understanding of physics. Quasars, for instance, are incredibly bright and distant objects believed to be powered by accreting supermassive black holes at the centers of young galaxies. They emit energy across the electromagnetic spectrum and can be used to study the early universe. Another exotic phenomenon is the blazar. They give off energy in all kinds of ways and help us learn about the early universe. Another strange thing is the blazar, a type of active galaxy whose jet is directed almost towards Earth, making it appear exceptionally bright. Pulsars, rapidly spinning neutron stars that emit beams of radiation, are yet another fascinating object. They help us study extreme states of matter and test the ideas of general relativity. Let's not ignore the smaller aspects of our universe, like planets. The process of planet formation and the exploration of our solar system and beyond represent a frontier of astronomical research. From the birth of planets to the hunt for habitable exoplanets, our understanding of these celestial bodies has significantly evolved. Planets start out as clouds of gas and dust that swirl around new stars. These clouds are called protoplanetary disks. As the dust and ice bits stick together, they grow bigger and bigger until they become planetesimals, which are like baby planets. Then, these planetesimals collide with each other and make bigger planets, called protoplanets. NASA's James Webb Space Telescope has provided crucial insights into this process, particularly concerning the role of water and icy pebbles in planet formation. Observations have confirmed that icy pebbles drifting from the colder outer regions of protoplanetary disks toward the star release water vapor as they pass the snow line, where ice transitions to vapor. This movement of ice bits is important for making rocky planets, like Earth, because it brings both solid and liquid materials to them. Our exploration of the solar system has been marked by numerous landmark missions, each contributing to our understanding of planetary environments. From the early days of the Voyager probes to the recent Mars missions, such as the Perseverance rover, our knowledge of planets, moons, and other celestial objects within our solar system has expanded exponentially. These missions have not only provided detailed information about planetary surfaces, atmospheres, and geology, but also insights into potential habitability and the history of our solar system. The discovery of exoplanets, planets orbiting stars outside our solar system, has been a significant development in astronomy. With advanced telescopes like the Kepler Space Telescope and the Trans-Sighting Exoplanet Survey Satellite, TESS, thousands of exoplanets have been identified, many in the habitable zone of their parent stars, where conditions might be right for liquid water, a key ingredient for life as we know it. One of the most surprising things that they have found is that rocky planets can form in many different places, even around stars that are very active and energetic. This goes against what we used to think, that rocky planets mostly formed around calm and low-mass stars. Understanding these diverse environments provides insights into why exoplanetary systems are as varied as they are, potentially broadening the search for habitable worlds. Studying planets is a fascinating and ever-changing field. Every time we find something new, we learn more about how planets work and what they can tell us. It also brings us closer to answering the profound question of whether we are alone in the universe. But there is more to the universe than meets the eye. Most of the universe is made of dark matter and dark energy, which we can't see or touch. Dark matter holds galaxies together with its gravity, and dark energy pushes the universe to expand faster and faster, defying our physics. Dark matter and dark energy are two of the biggest mysteries in modern cosmology. Dark matter and dark energy are two of the most enigmatic concepts in modern astrophysics, together constituting about 95% of the universe's total mass energy content. Dark matter, which is conditional through its gravitational effects on visible matter, galaxies, and the large-scale structure of the universe, dodges direct detection. Recent studies suggest a link between dark matter and the cosmic web, the large-scale structure of the universe, potentially unlocking new insights into its nature. Dark energy, responsible for the accelerated expansion of the universe, remains even more mysterious. While its nature and properties are largely unknown, it is a significant factor in cosmological models, impacting the universe's fate. Understanding these dark components is critical for a complete picture of the universe's composition and evolution. Unifying the two foundational theories of physics, quantum mechanics and general relativity, into a single framework is one of the most ambitious goals in physics. Quantum mechanics tells us how tiny things like atoms and electrons behave, while general relativity tells us how big things like stars and galaxies bend space and time. However, these theories are fundamentally incompatible with each other, creating a significant challenge in developing a unified theory of everything. Recent efforts have introduced new approaches to this challenge. Some physicists propose that spacetime does not need to be quantized. Instead, they suggest the presence of random fluctuations in spacetime curvature, which could be experimentally verified. These theories try to make sense of both the quantum and the classical aspects of space and time, and they might help us discover new things about them. Other theoretical approaches, such as Stephen Wolfram's work, hypothesize that the universe is like a giant computer program running on simple rules, leading to emergent properties like relativity and quantum mechanics. This approach suggests that these fundamental physics pillars are essentially the same phenomena, just seen from different angles, potentially offering new insights into the nature of the universe. The concepts of time and space, condensed in the theory of spacetime, are central to our understanding of the universe. Spacetime is a four-dimensional continuum, combining the three dimensions of space with the fourth dimension of time. This theory, central to general relativity, describes how massive objects bend the fabric of spacetime, leading to the phenomenon of gravity. Wormholes, hypothetical structures linking dissimilar points in spacetime, are a fascinating but speculative concept. If they exist, wormholes could allow for shortcuts through spacetime, potentially even enabling time travel. However, their existence remains purely theoretical, and the practical challenges, including the need for exotic matter to stabilize them, make them a subject of ongoing debate and research. The mysteries and theoretical concepts of dark matter, dark energy, the theory of everything, and spacetime represent the cutting edge of physics and cosmology. These topics not only challenge what we know, but also make us want to learn more. Now enough of what happened in history. What is the fate of us, and where, and how will this end? Well, scientists have different ideas about this, based on what they know about physics, dark matter, energy, and how fast the universe is growing. At the same time, humans are exploring space and making new technologies, hoping to learn more and see new things. The most common idea is the Big Freeze. This means the universe will keep growing bigger and bigger until everything is far apart and cold. There will be no new stars, no light, and no heat. Everything will stop moving and become a dark void. Another idea is the Big Rip. This means the universe will grow so fast that it will break apart. Dark energy will make everything fly away from each other, even atoms. Nothing will stay together. The heat death idea is similar to the Big Freeze, but it says that the universe will reach a point where there is no heat left to make anything happen. Everything will be the same temperature and nothing will change. Even though these ideas sound scary, we will explore more of space and find out about dark matter and energy, how far they can go, and if they can live on other planets. The future of the universe is both amazing and mysterious. It includes both the huge scale of the cosmos and the human desire to discover. Carl Sagan once said, "The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself." As we learn more and do more, we will find out new things that will surprise and inspire us. Let's keep being curious, humble, and eager to learn. The universe awaits. Ever notice how the night sky feels bigger than you? Like the stars are slowly drifting apart, stretching the constellations ever thinner. As it turns out, that's not just your imagination. That's the universe itself, expanding at a mind-boggling pace. And the only thing we have to explain is a mysterious force we call dark energy. Dark energy is a term that sounds mysterious and intriguing, and for good reason. It refers to an unknown form of energy that fills the entire universe. It makes up about 68% of the universe's total energy, and it has a strange effect. It pushes everything apart, overcoming gravity and accelerating the expansion of the universe. This mysterious energy, which seems to be the same everywhere, defies our conventional understanding of how gravity works and challenges us to rethink the nature of the universe. The idea of dark energy came from a surprising discovery in the late 1990s. Astronomers, who were expecting to find evidence that the universe's expansion was slowing down, were shocked when their observations of distant exploding stars called supernovae showed the opposite. The supernovae were dimmer than expected, which meant they were farther away than they should be. This implied that the universe was not only expanding, but also speeding up. This unexpected acceleration suggested the existence of an unseen force, later named dark energy. This discovery changed the way we view the universe and made us realize that we don't know what most of it is made of. Dark energy is one of the most important topics in cosmology and astrophysics, the fields of science that study the origin, structure, and evolution of the universe. Its discovery has profound implications for our understanding of the Big Bang Theory and the future of the universe. The void filler also challenges the foundations of Einstein's theory of general relativity. the best theory we have to describe gravity and the curvature of space and time. Dark energy forces us to consider new physics that could explain its mysterious properties. Understanding dark energy is essential for solving one of the biggest puzzles of the universe. What is its ultimate fate, and what are the laws that govern its expansion? Today, we think that dark energy makes up about 68% of the total energy in the observable universe, more than both normal matter and dark matter. But we still don't know what it is. Various theories propose that it could be a constant energy density filling space uniformly, or dynamic quantities, like scalar fields that vary in time and space. But none of them have been proven yet. Join us on this journey into the unknown as we seek answers to one of the greatest mysteries of the universe: dark energy, the void filler. The universe started from a single point smaller than an atom, and then exploded into existence 13.8 billion years ago. This is the essence of the Big Bang Theory, which was first proposed by Georges Lemaitre in 1927. He suggested that the universe was expanding from this tiny, dense point, and that we could trace its history by looking back in time. This idea was later confirmed by Edwin Hubble, who observed that galaxies were moving away from us, and that the farther they were, the faster they were receding. This means that the universe was once much smaller and hotter, and has been stretching and cooling ever since. In the beginning, the universe was a soup of particles and energy, which eventually formed atoms, stars, and galaxies as it expanded. But what makes the universe expand? And how does gravity fit into the picture? These are some of the questions that Albert Einstein tried to answer with his theory of general relativity, which he developed in 1915. This theory changed our view of gravity from being a force that pulls objects together to a property of the curvature of spacetime determined by mass and energy. Einstein himself initially resisted the idea of an expanding universe, introducing the cosmological constant, lambda, as a fix to maintain a static model. However, subsequent observations of the expanding universe affirm that his original equations, without the cosmological constant, correctly described a dynamic cosmos. The cosmological constant, lambda, introduced by Einstein to his field equations of general relativity, was initially meant to counteract gravity and achieve a static universe. This addition was made under the then common belief that the universe was static and unchanging. However, with Hubble's discovery of the expanding universe, the need for lambda was seemingly negated, leading Einstein to famously refer to it as his biggest blunder. Decades later, this blunder gained new relevance with the discovery of the universe's accelerated expansion. But maybe Einstein was too quick to dismiss the cosmological constant. The cosmological constant was revisited as a possible explanation for this phenomenon, suggesting that lambda represents a form of energy inherent to space itself, dark energy. This marked a significant shift in cosmological thinking, restoring the cosmological constant as a vital component in the understanding of the universe's expansion. Dark energy, a term coined in the late 20th century, refers to the mysterious force driving the accelerated expansion of the universe. This concept emerged from observations that distant supernovae were fainter than expected, indicating that the universe's expansion was speeding up, not slowing down as gravity alone would suggest. This acceleration started roughly 5 billion years after the Big Bang, implying the existence of a repulsive force overcoming gravitational attraction. Dark energy, which constitutes about 68% of the universe, fits this role, acting in opposition to gravity. The lambda CDM model, the current standard model of cosmology, incorporates dark energy as a critical component, often associated with the cosmological constant. The exact nature of dark energy remains one of the most profound mysteries in physics, challenging our understanding of fundamental forces and the ultimate fate of the universe. The discovery of dark energy has opened up new possibilities and challenges for our understanding of the universe's fate. It suggests that the universe could keep expanding forever, becoming colder, darker, and emptier. This raises new questions and puzzles for theoretical physics and cosmology, as we try to figure out what dark energy is and what it means for the nature of reality itself. The evidence for the existence of dark energy, a mysterious force driving the accelerating expansion of the universe, primarily comes from several key astronomical observations. Let's start with the redshift of galaxies. This is the phenomenon where the light from distant galaxies appears to be shifted towards the red end of the spectrum, indicating that they are moving away from us. This was discovered by Edwin Hubble in the early 20th century, and he found a simple rule: the farther a galaxy is, the faster it is receding. This means that the universe is expanding, like a balloon being inflated. But there is a twist. The expansion is not constant, but is accelerating. This was a surprise, because we expected that gravity would slow down the expansion over time. It was this unexpected discovery that the expansion is accelerating that led to the hypothesis of dark energy. The next piece of evidence comes from the study of supernovae. These are massive stars that explode at the end of their lives, releasing a huge amount of light. Some of these supernovae, called Type 1a, are very useful for measuring distances in space because they always have the same brightness. By comparing how bright they appear to us with how bright they actually are, we can tell how far away they are. In the late 1990s, astronomers observed some distant Type 1a supernovae and found something shocking. They were dimmer than expected. This means that they were farther away than they should be, which means that the universe was expanding faster than we thought. This was the first direct evidence for dark energy, and it stunned the scientific community. The third piece of evidence comes from the cosmic microwave background, or CMB. This is the faint glow of radiation that fills the universe, and it is the oldest light we can see. It was emitted when the universe was only 380,000 years old, and it contains a wealth of information about the early universe. By measuring the tiny variations in the temperature and polarization of the CMB, we can learn about the composition and evolution of the universe. These measurements, especially by the WMAP and Planck satellites, have shown that the universe is flat and that it consists of 68% dark energy, 27% dark matter, and 5% ordinary matter. These numbers match the predictions of the Lambda CDM model, the current best model of the universe, which includes dark energy as a cosmological constant. The final piece of evidence comes from the large-scale structure of the universe, or how galaxies are distributed and clustered across vast distances. The structure of the universe reflects the history of cosmic expansion, and it can be studied through galaxy surveys and other methods. One of these methods is baryon acoustic oscillations, which are ripples in the density of matter that were imprinted by sound waves in the early universe. These ripples can be used as a standard ruler to measure distances in space, and they agree with a universe that has dark energy. The evidence for dark energy is strong, coming from different and independent sources of observation. Despite its subtle characteristics, several theoretical models attempt to explain its properties and behavior. However, the nature of dark energy remains a mystery, one that challenges our understanding of the universe and its fate. The nature of dark energy remains one of the greatest enigmas in modern cosmology. We have seen that there is strong evidence for the existence of dark energy, a mysterious force that is making the universe expand faster and faster. But its nature and how it affects the fate of the universe are some of the questions that scientists are trying to answer. However, they are not easy to answer. In fact, they are some of the most difficult and fascinating questions in modern physics. Let's explore some of the possible theories and models that attempt to explain dark energy as well as some of the challenges and paradoxes that they face. One of the theoretical models that proposes a form of dark energy is called quintessence, which suggests that dark energy is a dynamic field, like a fluid that fills the universe. Unlike the cosmological constant, which is a fixed and constant energy density, quintessence can change over time, depending on its potential energy. This means that the acceleration of the universe's expansion could vary in the future, either increasing or decreasing. Quintessence is like a roller coaster, where the speed of the ride depends on the shape of the track. Another model is called phantom energy, which is even more extreme than quintessence. Phantom energy assumes that dark energy has a negative pressure that is greater than its energy density, which makes it violate some of the basic laws of physics. This leads to a scenario where the universe ends in a big rip, where the force of dark energy becomes so strong that it rips apart everything in the universe, from galaxies to atoms and even space-time itself. Phantom energy is like a bomb that is ticking faster and faster until it explodes and destroys everything. A third theoretical model is called K-essence, which focuses on modifying the kinetic energy of dark energy. K-essence theories propose a form of energy that behaves differently from normal matter and energy, and that could have played a role in the early universe. K-essence could have evolved in such a way that it now drives cosmic acceleration without violating the conservation of energy. K-essence is like a chameleon, which can change its color and appearance depending on the environment. Moving on, we come back to the cosmological constant, which is the simplest and most popular explanation for dark energy. The cosmological constant is a term that was introduced by Einstein in his theory of general relativity, but he later called it his biggest blunder. But maybe he was too harsh on himself, because the cosmological constant could be the energy of empty space itself, which is pushing the universe apart. However, the cosmological constant also raises some questions, especially the fine-tuning problem, which wonders why the value of the cosmological constant is so incredibly small, yet not zero. The cosmological constant is like a needle in a haystack. It is very hard to find and explain. Another mystery is the coincidence problem, which asks why the energy density of dark matter and dark energy is nearly equal today, despite their vastly different evolutionary histories. The coincidence problem is like a magic trick that seems impossible and amazing, but has a secret behind it. The quest to understand dark energy is a journey that takes us to the frontiers of physics and cosmology. It is a journey that involves exploring different theories and models, as well as facing some of the most profound and perplexing questions and paradoxes. But will the universe keep expanding forever? Or will it end in a catastrophic event? The fate of the universe hinges on the nature of dark energy. If dark energy remains constant, as in the cosmological constant scenario, the universe might continue to expand forever, leading to a big freeze. In the big freeze, the universe becomes a cold, dark, and empty place. This could happen if dark energy stays constant, like the cosmological constant that Einstein proposed and later rejected. In this case, the universe would continue to expand indefinitely, and galaxies would drift away from each other until they become invisible. The temperature of the universe would approach absolute zero, and no life or activity could exist. Alternatively, if dark energy increases in strength, it could lead to the Big Rip. In this scenario, dark energy becomes so dominant that it overwhelms all other forces, including gravity, tearing apart galaxies, stars, planets, and eventually, the very fabric of space-time itself. Lastly, there is death, a concept where the universe reaches a state of maximum entropy. This is based on the second law of thermodynamics, which states that the disorder of a system always increases. In this case, the universe would evolve to a state where everything has the same temperature and no energy can be used for work. The universe would become a uniform soup of particles with no structure or variation. The role of dark energy is pivotal in these scenarios. Its mysterious nature, whether it's a constant force, like the cosmological constant, or a dynamic field that changes over time, will dictate the universe's trajectory. Recent studies, like those from the Dark Energy Survey, indicate that the nature of dark energy might be more complex than previously thought, possibly varying over the lifetime of the universe. This enigmatic force propelling the universe's accelerating expansion is being investigated through various groundbreaking research projects and experiments, leveraging advanced technology and challenging our understanding of physics. One of the foremost projects in this domain is the Pantheon Plus analysis. This study, based on the largest data set of its kind, includes over 1,500 Type 1a supernovae. These supernovae, due to their nearly uniform intrinsic brightness, serve as cosmic markers, revealing the universe's expansion rate across different epochs. This research has refined our understanding of dark energy and dark matter's role in cosmic evolution, suggesting that 66.2% of the universe manifests as dark energy. Another significant endeavor is the Dark Energy Survey, DES, which uses a 570-megapixel dark energy camera on the Victor M. Blanco 4-meter telescope in Chile. DES aims to understand the nature of dark energy by studying how it shapes the large-scale structure of the universe over time. Researchers analyze galaxy clustering and weak gravitational lensing to infer the distribution of dark matter and the impact of dark energy. This survey has produced the most precise measurements of the universe's composition and growth to date. The European Space Agency, with contributions from NASA, launched the Euclid Space Telescope to investigate dark matter and dark energy. Euclid aims to create a detailed map of roughly 1/3 of the sky, documenting billions of galaxies up to 10 billion light-years away. The mission will use a large format, visible light camera, and a near-infrared spectrometer and photometer to measure the redshift of distant galaxies. These projects and experiments rely on advanced technology to process the huge amounts of data they collect. They use high-performance computing, artificial intelligence, and sophisticated imaging technology to analyze and interpret the data. These technologies enable us to explore the universe with unprecedented detail and precision. Understanding dark energy is not only important for cosmology, but also for theoretical physics. It challenges the existing theories of physics, such as Einstein's general theory of relativity. It could lead to new discoveries, such as new particles or forces, and might even require us to revise the fundamental laws of physics. Researchers from Ohio State and other institutions have been leading this research, using instruments like the Hubble Space Telescope and contributing to projects like DES and SDSS. The results of these studies could not only enhance our understanding of the universe, but also transform the field of physics. Carl Sagan once stated, "Somewhere something incredible is waiting to be known." And dark energy, making up the majority of the universe's energy, is a profound reminder of how much remains to be discovered. As we peer into the depths of space, we are humbled by the realization that most of the universe is made of forces and entities beyond our current comprehension. Nature is the art of God, and we are drawn to the unknown, to the mysteries of the universe that await our discovery. Let's keep on exploring and learning to challenge ourselves and our understanding of reality. 4 billion years from now, something amazing will happen in our night sky. Something that will make you feel like you're in a sci-fi movie. Our night sky will be transformed by a cosmic event unlike any other. Our home galaxy, the Milky Way, will collide with the Andromeda Galaxy, our closest neighbor. This is not a wild guess, but a scientific certainty. It's the fate of our galaxy and our place in the universe. How would you feel if you could see Andromeda, a galaxy that's now 2.5 million light-years away, growing closer and closer every night? It's moving towards us at a mind-blowing speed of 68 miles per second. That's faster than a bullet or even a rocket. It's fast enough to travel from Earth to the Moon in an hour. When these two galaxies meet, it will be a spectacular show of stars, planets, and dust. They will swirl around each other, pulled by the force of gravity. Some stars will become new neighbors, while others will be thrown into the depths of space. But don't worry, the chances of stars crashing into each other are very low. The most dramatic part of this merger will be the clash of the supermassive black holes at the centers of both galaxies. These are the most powerful objects in the universe, and when they merge, they will release a huge amount of energy and possibly create a new kind of galaxy. This galactic merger is not just a cool thing to watch, but a reminder of how amazing and dynamic our universe is. For thousands of years, humans have looked at the Milky Way and wondered about its secrets and mysteries. In the far future, our descendants, if they are still around, will look at a new night sky, one that's the result of the merger of the Milky Way and Andromeda. But as we think about this distant future, we also realize how small we are in the grand scheme of things. The Milky Way and Andromeda are just two of the billions of galaxies in the universe, each with their own stories and histories. They are following a path that was set billions of years ago, and nothing can change it. This inevitable collision is not just the story of two galaxies, but a chapter in the bigger story of the universe. Now that we have seen the amazing future of our galaxy, the Milky Way, let's take a closer look at what it is like right now. The Milky Way is a beautiful spiral galaxy with a long bar of stars in the middle and four main arms that curl around it. The arms are brighter than the rest of the galaxy because they have more young and hot stars. The bar and the arms make up the disk of the galaxy, which is where most of the stars, dust, and gas are. But the disk is not the only part of the galaxy. There is also a bulge in the center where a supermassive black hole lurks. This black hole, called Sagittarius A star, is surrounded by a ring of very hot gas. The bulge also has many old stars and clusters of stars, called globular clusters. Beyond the disk and the bulge, there is a halo of stars that surrounds the galaxy. The halo is much bigger than the disk and extends over 150,000 light-years from the center. The halo has many old and faint stars, as well as most of the globular clusters. It is also where most of the dark matter is, which is something we can't see, but we know it's there because it affects the gravity of the galaxy. The Milky Way is about 100,000 light-years across, which means it would take light 100,000 years to travel from one end to the other. It has hundreds of billions of stars, and our Sun is just one of them. The Sun is about 30,000 light-years away from the center of the galaxy in one of the spiral arms. The first person to measure the size of the galaxy was Harlow Shapley in 1917. He was the first to realize how big the Milky Way really is. The Milky Way, like all galaxies, has a long and complex history. It was born from a huge cloud of gas and dust about 13 billion years ago, soon after the Big Bang. The cloud collapsed under its own gravity and formed stars and planets. As the galaxy grew, it also changed. It interacted with other galaxies, sometimes merging with them, and sometimes eating them. The Milky Way has swallowed many smaller galaxies in the past, and some of them are still visible as streams of stars in the halo. But why does the existence of the Milky Way matter? One thing is that it is our home and our connection to the universe. By studying the Milky Way, we can learn more about how galaxies form, evolve, and interact. The Milky Way is not done changing. It is still making new stars, but not as fast as before. It is heading towards a collision, and in about 4 billion years, Andromeda, and the Milky Way will meet and merge into a new galaxy. This new galaxy might look very different from the Milky Way we know today. The collision between two giant swirls of stars, planets, and dust is inevitable, and nothing can stop them. It's not a matter of if, but when. The Andromeda Galaxy is coming towards us at a mind-blowing speed of nearly 250,000 miles per hour. That's faster than a bullet or even a rocket. It's fast enough to travel from Earth to the Moon in an hour. When these two galaxies meet, they will swirl around each other, pulled by the force of gravity. Some stars will become new neighbors, while others will be thrown into the depths of space. But don't worry, the chances of stars crashing into each other are very low. The collision will not end quickly. It will take another 2 billion years for the galaxies to fully merge and form a new galaxy. This new galaxy will look very different from the Milky Way or Andromeda. It will be a giant elliptical galaxy with no spiral arms and no disk. The stars within will be scattered into new orbits, creating a galaxy different from any spiral or elliptical galaxy we see today. The collision might also involve another galaxy, the Triangulum Galaxy, which could join the merger and become part of the new galaxy. But what's the fate of our solar system in this galactic merger? Well, the answer is not very clear. Some scientists think that our solar system will be pushed farther away from the center of the new galaxy, about 3 times as far as it is now. Others think that it could be kicked out of the new galaxy altogether. But either way, these events will not affect the solar system itself unless we do something to change it. By the time of the collision, the sun will be so bright that the Earth will be too hot for life anyway. The collision will also have some effects on the stars and the black holes in both galaxies. The stars in the disks of the galaxies will be squeezed by the gas and dust and might form new stars. But this will not be very strong compared to other galaxy mergers. The black holes in the centers of the galaxies will also play a big role. They will spiral toward each other and eventually merge. This will release a huge amount of energy and might create a new kind of galaxy core. The Milky Way-Andromeda collision is not just a cool thing to watch, but a reminder of how amazing and dynamic our universe is. By studying this collision, we can learn about our own origins and our place in the cosmos. The universe is full of wonders, and one of them is the cycle of birth and death of stars and galaxies. This process, primarily driven by hydrogen and the laws of physics, unfolds over billions of years, eventually leading to a galaxy's demise. Star formation begins in the dark and cold expanses of interstellar space, within giant molecular clouds composed predominantly of hydrogen gas. These clouds, sometimes spanning over 100 light-years, contain up to several million solar masses. Under the influence of gravity, these clouds undergo gravitational collapse, breaking into smaller, denser regions called Bok globules, which can form stars. Inside these pieces, the gas and dust keep falling and heating up, creating a hot core called a protostar. The protostar grows bigger and hotter by attracting more gas and dust. For stars like our Sun, the core temperature ultimately reaches around 10 million Kelvin, igniting nuclear fusion, where hydrogen atoms fuse to form helium, releasing immense amounts of energy. This energy makes the star shine. A star's life is a balance between two forces: the energy from the nuclear reaction that pushes outward and the gravity that pulls inward. At first, a star uses hydrogen in its core for the nuclear reaction, but it runs out of it eventually. Then it starts to use helium and other heavier elements. For a high-mass star, this process continues up the periodic table until silicon fuses into iron. However, fusing iron consumes energy instead of releasing it, leading to the core's collapse and ultimately a supernova, an explosion that outshines entire galaxies and scatters elements across the cosmos. As galaxies age, their ability to form new stars diminishes because they run out of the material they need to make new stars, mainly hydrogen. As galaxies get older, they use up most of their hydrogen to make stars, planets, and other things. At some point, a galaxy has no more gas to form new stars, and its star formation rate drops. When a galaxy stops making new stars, it enters the final stage of its life. Without new stars to replace those that die, the galaxy will gradually become dimmer. The remaining stars, mostly long-lived red dwarfs and remnants like white dwarfs, neutron stars, and black holes, will continue to shine, but their numbers will steadily decrease. Over vast timescales, these will also fade away, leaving the galaxy dark and devoid of the lively and colorful starlight that once made it beautiful. The cycle of star formation and galactic death is a story of change and contrast in the universe. It is a story of how the universe is amazing, but also fleeting. As we contemplate the future of our galaxy, it is crucial to understand the final stages of the Milky Way Andromeda merger and the birth of Milkomeda, or Milkdromeda. The collision between the Milky Way and the Andromeda galaxy will be a process rather than a singular event. They won't crash into each other in one go. Approaching us at nearly 250,000 miles per hour, Andromeda's collision with the Milky Way will begin with a series of pulls and tugs on each other with their gravity. This will make them pass through each other, stretching out long trails of stars and other material. The process will go on for billions of years, and it will make both galaxies look very different. As the galaxies dance, they will miss each other a few times, each time distorting their shapes and scattering their stars. Some of the stars, maybe even our Sun, will switch places between the galaxies. The first big hit will change the galaxies a lot, making new stars as the gas in their disks gets squeezed. After the first big hit, the Milky Way and Andromeda will take another 2 billion years to fully join together. This merger will eventually reshape the two spiral galaxies into a single elliptical galaxy. This new galaxy, Milkomeda, will lack the spiral arms that we see now. It will be more round and smooth, with stars spread out evenly and a less crowded center than other round galaxies. The merged galaxy will likely host a mix of stars from both original galaxies, now in randomized orbits, resulting in a vastly different night sky than we see today. The cores of the Milky Way and Andromeda, each with their own supermassive black hole, will eventually spiral towards each other. They might join together, making a very bright and powerful core. The story ends with the new galaxy in form, but the Milky Way and Andromeda, as we know them, are just the beginning of a new chapter in the story of our local universe. Over time, Milkomeda may continue to evolve, possibly merging with other nearby galaxies, including the Triangulum Galaxy M33, and forming an even larger galactic assembly. In the far future, when the stars of Milkomeda and other galaxies run out of fuel, the galaxy will enter a time when most of the bright stars have died, leaving behind only white dwarfs, neutron stars, and black holes. These leftovers will slowly cool down and dim over trillions of years. As the universe gets older, even these leftovers will vanish because of things like proton decay. The universe will transition into the black hole era, where only black holes remain, eventually evaporating through Hawking radiation, leading to the dark era, characterized by a cold, dark, and empty universe devoid of any substantial structures. The expansion of the universe, a key aspect of Big Bang cosmology, continues to accelerate due to dark energy. This acceleration will lead to an increasingly isolated universe. As space expands, galaxies beyond our local group will move away from us at speeds so great that their light will never reach us. This isolation will intensify over time. eventually leading to a universe where galaxies are so far apart that they are essentially alone in their observable universe. This phenomenon, often referred to as cosmic loneliness, highlights a future where galaxies are so distant from each other that intergalactic travel or communication becomes impossible. The huge space between them will make them like islands of galaxies, each unaware of the others. In this future, any life that might exist will be stuck in its own galaxy, with no way to see or reach the rest of the universe. The universe's expansion, caused by dark energy, not only shapes the universe but also dooms its living beings to deep loneliness. The far future of the universe is one of gradual decay and increasing isolation, showing how time and physics are unstoppable. The universe we know today, full of galaxies and stars, will one day become a cold, dark, and lonely place. The future of galaxies, including our new one, Milky Way, depends on how the universe keeps expanding and what happens to the stars. The Milky Way and Andromeda are going to crash into each other. This is not the only time that galaxies do that. Interactions like these play a fundamental role in the growth and evolution of galaxies. Such processes can lead to intense bursts of star formation, reshaping the galaxy's structures and altering their star populations. These interactions provide crucial insights into the dynamics of galaxies, the role of dark matter, and the process of star formation. By studying these mergers, astronomers gain a deeper understanding of how galaxies evolve and the cosmic forces that drive these changes. The death of galaxies, including our Milky Way, makes us think that nothing in the universe lasts forever, even the things that look like they do. This can make us feel small and humble, as we realize how short our lives are compared to the universe's age. It also makes us wonder about what existence is and what will happen to the universe. As galaxies move away and stars die, the universe will look very different, and we might not recognize it. This loneliness makes us think about how alone we might be in the future and what it means to exist in a universe that doesn't care about us. The future of Earth depends on how the sun changes and what it does to our environment. The sun will use up its fuel, grow bigger and bigger, and turn into a white dwarf. Long before the predicted galactic collision, Earth will have faced extreme environmental changes due to the sun's evolution. The increasing luminosity of the sun, potentially causing a runaway greenhouse effect, will lead to the loss of Earth's oceans and a significant alteration of its atmosphere. The story of humanity, compared to the story of the universe, is a short and sad one. As we learn more about the universe, we also think more about what we mean. The Milky Way and Andromeda will crash into each other, but this will happen billions of years later. This crash shows us how the universe is always changing and growing. It makes us wonder about what we do and make in this big and unstoppable universe. The things we do and learn in space and astronomy are very important in enhancing our understanding of these cosmic events. Future space missions, telescopes, and scientific research will continue to refine our models of the universe, offering deeper insights into the mechanics of galaxies, the behavior of dark matter and dark energy, and the potential for life beyond Earth. As we expand our knowledge and capabilities, we also expand the possibilities for humanity's future, potentially extending our reach beyond our solar system and contributing to a legacy that outlives our planet's lifespan. In the words of Marcus Aurelius, "He who lives in harmony with himself lives in harmony with the universe." Our understanding of the universe may be limited, but our quest to understand it is limitless. As we continue to learn and grow, we may find new answers and new questions, but we may also find new ways to appreciate and celebrate the beauty and diversity of the universe. What if the world we live in was not the only one possible? What if there were other worlds where the basic rules of physics were different? Where time could flow backwards, gravity could repel instead of attract, and light could be touched and felt, This idea is a way of opening our minds to the amazing universe we are part of, where such strange rules do not apply, but where reality is still astonishing. We have been exploring this universe with wonder and curiosity, making incredible discoveries along the way. One of them is the possible detection of a rogue black hole, as announced in January 2024. This discovery started in 2011, when a huge, dark object crossed the path between Earth and a star near the center of our galaxy. The star became brighter for 270 days, as its light was bent and magnified by the object's mass through a phenomenon called gravitational microlensing. This event caught the attention of astronomers who thought that the object could be a black hole roaming alone, a rare occurrence in our galaxy where black holes are usually paired with other stars. Using the Hubble Space Telescope, scientists carefully tracked the star's position for 6 years and estimated that the intruder is likely a black hole between 5.8 and 8.4 times the mass of our Sun. Another amazing discovery comes from the Beta Pictoris system, a young system of planets only 63 light-years away from us. Here, astronomers using NASA's James Webb Space Telescope found a new feature in the system, a branch of dust with a sharp angle resembling a cat's tail that extends from the second ring of debris. This feature, never observed before, adds to the complexity of Beta Pictoris, which is already known for its multiple rings, comets, and 2 planets that have been imaged. From the cosmic wonders that challenge our comprehension to the influence of space exploration on human culture, let's discover the beauty and mystery of our incredible universe. The universe is full of wonders and mysteries that we are still trying to understand. Some of the most amazing and bizarre things in the cosmos are rogue planets, neutron stars, and quasars. Let's take a closer look at each of these fascinating objects and how they reveal the diversity and complexity of the universe. Essentially, a rogue planet is a lonely and dark world drifting in vast and empty space, while a star system with planets and moons shines brightly nearby. A neutron star is a tiny and dense ball spinning like a top and emitting powerful pulses of radio waves, while the Sun, a much larger and slower star, glows steadily in the background. And finally, the quasars is the fiery disk, radiating more light and energy than 1,000 galaxies, while the rest of the universe looks dim and faint in comparison. But there is much more to these cosmic bodies. Rogue planets have no stars to orbit. They are like cosmic wanderers, roaming the galaxy on their own. They become rogue when ejected from their original star system by gravitational interactions with other planets or stars. Others may have formed in isolation, far away from any star. Scientists estimate that there could be trillions of rogue planets in our galaxy alone, and some of them may even have the right conditions to support life. The Nancy Grace Roman Space Telescope, which is planned to launch in 2027, will use a technique called microlensing to detect these elusive planets. Microlensing happens when a rogue planet passes in front of a distant star and acts like a lens, bending and amplifying the star's light. By observing these microlensing events, the telescope will be able to measure the mass and distance of the rogue planet. The telescope may find up to 400 rogue planets that are similar in size to Earth. Neutron stars are the leftovers of massive stars that have exploded in supernovas. They are incredibly dense and compact, with a mass of about 1.4 times that of the Sun squeezed into a sphere of only 20 kilometers in diameter. That means a teaspoon of neutron star material would weigh billions of tons. Neutron stars also spin very fast, up to hundreds of times per second, and have very strong magnetic fields, up to 1 trillion times stronger than Earth's. One of the most extreme neutron stars ever discovered rotates at a staggering speed of 716 times per second, or 24% of the speed of light. Neutron stars are also the source of pulsars, which are beams of radio waves that sweep across the sky like lighthouses. Pulsars can be used as cosmic clocks because they are very precise and stable in their rotation. Quasars are the brightest and most energetic objects in the universe. They are powered by supermassive black holes at the centers of galaxies, which devour huge amounts of gas and dust. As the material falls into the black hole, it forms a hot and turbulent disk that emits intense radiation across the electromagnetic spectrum, from radio waves to gamma rays. Quasars can outshine their entire host galaxies, making them visible from billions of light-years away. One of the first quasars ever discovered, 3C 273, is so bright that it appears like a star in the night sky, even though it is actually 2.4 billion light-years away. Quasars are also very hot, with temperatures of hundreds of thousands of degrees, much hotter than the Sun. The James Webb Space Telescope, launched in 2021, will study quasars in unprecedented detail and reveal how they affect their surroundings and the evolution of the universe. Quasars are especially important for understanding the period of cosmic reionization, when the first stars and galaxies ionized the intergalactic medium and ended the cosmic dark ages. The cosmos has always captivated and shaped human cultures in different ways. From ancient times to the present day, the stars and planets have influenced how people navigate, live, and create. Space is not only a physical realm, but also a cultural one. In the past, many cultures looked up to the sky for guidance and meaning. The ancient Polynesians were expert navigators who used the stars to sail across the vast Pacific Ocean. Their deep understanding of celestial patterns enabled them to make remarkable voyages over thousands of miles. They reached faraway islands like Hawaii and settled there, thanks to their stellar knowledge. The ancient Egyptians also relied on the stars, especially Sirius, the brightest star in the night sky. They noticed that Sirius appeared just before the Nile River flooded every year, bringing life and fertility to their lands. They based their calendar and rituals on this cosmic cycle. This celestial observation was so critical that it became intertwined with their calendar and daily lives. Some of the oldest monuments in Europe, like Stonehenge in England and Newgrange in Ireland, were built by Neolithic people who aligned them with the sun's movements. These sites were more than just astronomical devices. They were also places of culture and worship, where people celebrated the seasons and honored their ancestors. The Maya civilization was another culture that had a deep interest in astronomy. They developed a complex calendar that tracked the cycles of the sun, the moon, and the planets. They paid special attention to Venus, which they associated with war, disease, and death. The Dresden Codex, an ancient Maya text, contains remarkably accurate astronomical tables, a proof of their extensive observational knowledge. In modern times, space exploration has opened new horizons for culture, art, and philosophy. We have gained a new perspective on space and ourselves, thanks to the images and discoveries from space missions. One of the most iconic images is the Earthrise, taken by the Apollo 8 astronauts in 1968. It shows our planet as a blue and green oasis in the blackness of space, reminding us of its beauty and vulnerability. The space race of the 20th century, which culminated in the moon landing in 1969, was not only a scientific and technological achievement, but also a cultural milestone. It inspired a sense of awe and unity among people around the world who witnessed the first human steps on another world. Space has also been a source of inspiration for many artists who have used it to express their imagination and creativity. Science fiction is a genre that explores the possibilities and challenges of space travel and alien life. Movies like 2001, A Space Odyssey, and Interstellar have challenged and expanded our imagination about what lies beyond Earth. Philosophically, the exploration of space has raised fundamental questions about our place in the universe, our understanding of time and space, and the future of humanity. It has influenced thinkers to ponder the ethical implications of space colonization and the potential discovery of extraterrestrial life. As you can see, space has had a significant and lasting impact on human culture and society. From influencing us to navigate, live, and create, it has also inspired us to wonder and explore. The universe is full of wonders and mysteries that we are still trying to understand. One of the biggest puzzles in astrophysics is dark energy. This is a mysterious force that makes the universe expand faster and faster over time. Dark energy accounts for about 68% of the total energy in the universe. But we don't know what it is or how it works. Many theories try to explain dark energy, but none of them have been proven yet. Some of them suggest that dark energy is a property of space itself, that it is related to a new form of matter or energy, or that it is a sign of extra dimensions or multiple universes. Speaking of multiple universes, another fascinating idea in astrophysics is the multiverse. This is the possibility that our universe is not the only one, but one of many, each with its own laws of physics and history. The multiverse concept challenges our notion of reality and raises questions about the origin and fate of our universe and the existence of other forms of life. Another mystery that astrophysicists are trying to solve is how supermassive black holes formed so early in the universe's history. These are black holes that are millions or billions of times more massive than the Sun, and they are found at the centers of galaxies, including our own. Some of them, called quasars, are so bright that they can be seen from billions of light years away. But how did they grow so big so fast when the universe was only a fraction of its current age? What were the conditions and processes that allowed such rapid accumulation of mass? But astrophysics is not only about mysteries, but also about debates and theories. One of the most controversial topics in astrophysics is dark matter. This is a type of matter that does not emit or reflect light but interacts with gravity. Dark matter makes up about 27% of the total matter and energy in the universe, but we don't know what it is made of. There are many candidates for dark matter particles, such as WIMPs, weakly interacting massive particles, or axions, but none of them have been detected yet. Alternatively, some physicists argue that dark matter is not a new form of matter, but a modification of gravity. A hot topic for us is the black hole information paradox. This is a conflict between quantum mechanics and general relativity, two of the most successful theories in physics. Quantum mechanics says that information cannot be lost or destroyed, but general relativity says that black holes can evaporate and disappear, taking their information with them. How can we resolve this paradox? Some physicists propose that black holes have firewalls, which are violent regions of energy that destroy anything that falls into them. Others suggest that black holes have holographic surfaces, which store their information on their boundaries. The next debate in astrophysics is about the cosmological principle. This is the assumption that the universe is the same everywhere on large scales, meaning that it is smooth and uniform. This principle is the basis of many cosmological models, but it may not be true. Recent observations show that the universe is expanding faster in some regions than in others, which could mean that the universe is not isotropic or the same in all directions. If the cosmological principle is wrong, we may need to rethink our understanding of the universe. Another question that we are trying to answer is how big and what shape the universe is. We can only see a part of the universe, which is about 93 billion light-years across, but the whole universe could be much bigger, or even infinite. We also don't know if the universe is flat, curved, or twisted, which affects how it will end. Will it keep expanding forever? Or will it collapse into a big crunch? Or will it rip apart into pieces? Scientists and astronomers are working hard to explore these questions using advanced technologies and observatories. Some of them are the James Webb Space Telescope, which was launched in 2021, and the Rubin Observatory, which will start operating in 2023. These instruments will collect a lot of data, which will help us learn more about dark matter, dark energy, and other cosmic mysteries. In this fascinating and exciting field, where we can explore some of the most profound questions about our universe, researchers and scientists cooperate with professionals from various other fields, such as chemists, biologists, and geologists, to study the connections between the cosmos and the Earth. The universe is a vast and mysterious place, and we are still trying to figure out how it works and what it looks like. While we are at it, our technologies are taking a leap as well. Space travel technology is changing rapidly, making things possible that we only dreamed of before. Some of these things are warp drives and wormholes, which could allow us to travel faster than light and across the universe. Warp drives are devices that would bend space-time around a spacecraft, creating a shortcut in space. Wormholes are like tunnels that connect two distant points in space-time, creating a shortcut in time. These ideas are very popular in science fiction, but they are also based on real physics. However, we don't know if they are feasible or how to create them. But some recent discoveries in physics give us some hope that we might be able to achieve them someday. But we don't have to wait for warp drives and wormholes to explore space. We already have many technologies that can help us travel faster and farther in space. For example, we have ion engines and nuclear engines, which are types of propulsion systems that use electric or nuclear power to accelerate a spacecraft. These engines are more efficient and powerful than conventional rockets, which use chemical fuel. They could help us reach the outer planets and beyond, saving us a lot of time and resources. We also have amazing technologies that help us live and work in space. One of them is the International Space Station, ISS, which is a huge orbiting laboratory where astronauts from different countries conduct scientific experiments and test new technologies. The ISS has been in space since 1998 and has been continuously occupied by humans since 2000. It is a great example of how we can cooperate and learn from each other in space. Another exciting technology is space tourism, which is the idea of sending ordinary people to space for fun and adventure. Several companies, such as SpaceX, Blue Origin, and Virgin Galactic, are working on making this possible. They are developing reusable rockets and spacecraft that can take tourists to the edge of space, or even to the ISS. But as we explore and enjoy space, we also have to think about the ethical issues that come with it. One of them is the colonization of other planets, which is the idea of creating permanent settlements on other worlds, such as the Moon or Mars. This could have many benefits, such as expanding our knowledge, resources, and survival options. But it could also have many risks, such as harming the environment, culture, and life of other planets if they exist. It could also create conflicts and inequalities among the colonists and the people on Earth, especially if some countries or groups try to claim or control more space than others. We have to make sure that we respect and protect the rights and interests of all beings and nations involved in space exploration and colonization. There's also the matter of ensuring that the benefits of space exploration and colonization are distributed equitably among all nations and peoples on Earth, preventing space from becoming the exclusive domain of wealthy nations and individuals. Space travel technology is an exciting and challenging field where we can discover new things and experience new adventures. But we also have to be responsible and ethical and consider the consequences and implications of our actions in space. Space is not only a physical place, but also a cultural and moral one. As we conclude our exploration into the mind-blowing universe, we are left with a sense of wonder and an ever-growing list of questions. From the enigmatic nature of dark energy and the possibility of multiverses to the ethical considerations of interstellar travel, our journey through the cosmos reveals just how much remains to be discovered and understood. But this journey is far from over. In the words of Carl Sagan, somewhere, something incredible is waiting to be known. Let us move forward together, with eyes wide open to the wonders of the universe and hearts filled with an unquenchable thirst for discovery. The cosmos awaits. What is the origin of everything we see in the night sky? This question has captivated humans for millennia, leading us to gaze upwards in wonder and curiosity. The night sky, a twinkling canvas of stars and galaxies, is our gateway to understanding the universe, a vast and complex entity that extends far beyond our planet. The universe is the totality of space, time, matter, and energy that exists. With its countless galaxies, stars, and planets, it is an ever-evolving mystery, one that encompasses the very fabric of time and space. It's a network where cosmic events unfold on scales unimaginable, and yet each part of this cosmic play is interconnected, interlacing a story of creation, transformation, and discovery. Exploring the universe's beginnings and how it works is more than just a hobby or a passing interest. It's part of what makes us human. Throughout history, we've always looked around us and asked, why and how? This quest for understanding is a deeply human trait, something that connects us across different cultures and eras. When we seek to understand the universe, we're following in the footsteps of countless others who have looked up at the stars and wondered about their place in it all. It's a shared human journey, one that's about satisfying our innate need to understand the world we live in and our role in it. By connecting the tiniest dots, we will have clues about our own origins and about how a planet called Earth could emerge in such a vast universe to support life. This exploration helps us see our world and our place in it with new eyes, reminding us that we're a small but unique part of a much larger, ever-changing universe. The story of the universe's formation and evolution is a remarkable journey through time and space. At its core is the Big Bang Theory, which describes how our universe expanded from an initial state of extremely high density and temperature. This concept was first proposed in 1927 by Georges Lemaire, a Roman Catholic priest and physicist. The Big Bang Theory is supported by a variety of cosmological models that explain the evolution of the observable universe from its earliest known periods through its subsequent large-scale form. These models are compatible with the Hubble-Lemaitre law, which observes that the farther away a galaxy is, the faster it is moving away from Earth. This expansion of the universe is a key feature of the Big Bang Theory, suggesting an increasingly concentrated cosmos preceded by a singularity where space and time lose meaning. In the first picosecond of cosmic time, we encounter the Planck epoch, a period where the established laws of physics may not have applied. This epoch saw the emergence of the four known fundamental interactions or forces: gravitation, electromagnetism, weak interactions, and strong interactions. This early period of the universe is understood through the extrapolation of known physical laws to extreme high temperatures, as practical experiments in particle physics are beyond our current capabilities. Following this initial expansion, the universe cooled enough for the formation of subatomic particles and later atoms. This led to the unequal abundances of matter and antimatter, known as baryon asymmetry, a phenomenon still not entirely understood. Primordial elements like hydrogen, helium, and lithium formed and later coalesced through gravity, leading to the formation of early stars and galaxies. In physical cosmology, cosmic inflation is the theory explaining the exponential expansion of space in the early universe. Believed to have occurred after the Big Bang, this concept was developed by physicists such as Alexei Starobinsky, Alan Guth, and Andrei Linde. Inflation explains the large-scale structure of the cosmos, with quantum fluctuations in the microscopic inflationary region being magnified to cosmic size. These became the seeds for the growth of structure in the universe. In the early universe, quantum fluctuations, especially those associated with the inflaton and gravitational fields at the onset of inflation, were pivotal. These fluctuations stretched across the universe due to its expansion and, amplified by gravitational instability, led to the formation of all cosmic structures. This theory is supported by astrophysical data, including findings from the Planck satellite. Integrating quantum field theory, the inflationary phase is hypothesized to be driven by a field known as the inflaton. Quantum field theory helps us understand how quantum fluctuations during this phase were projected onto cosmic scales, influencing the density and temperature variations that became the framework for the universe's structure. The universe has undergone significant changes over billions of years. For about 370,000 years after the Big Bang, various kinds of subatomic particles formed. The universe at this time was too hot for neutral atoms to exist, or for photons to travel far, making it an opaque plasma. After this period, known as recombination and decoupling, the universe became transparent. However, it was devoid of light sources, other than the cosmic microwave background radiation and occasional 21 centimeters radio emissions from hydrogen atoms. This period is known as the Cosmic Dark Ages. The cosmic microwave background, CMB, radiation is a crucial remnant of the early universe, holding immense significance in our understanding of cosmology. It is essentially the afterglow of the Big Bang, infusing the entire universe and acting as a cosmic time capsule. About 370,000 years after the Big Bang, the universe had expanded and cooled to a point where electrons could combine with nuclei to form neutral atoms. This era, known as recombination, led to a significant event. Photons, which had previously been trapped within the hot, dense plasma of the early universe, were suddenly free to travel through space. This freedom created a faint but pervasive glow across the cosmos, the CMB. By studying CMB's minute temperature variations, scientists have deduced vital statistics of the universe, such as its age, shape, and the amount of matter and dark energy it contains. The uniformity of the CMB across the sky also confirms our understanding of the universe's homogeneity on a large scale. Yet its subtle fluctuations hint at the seeds that grew into today's galaxies and cosmic structures. Moreover, the CMB is pivotal in confirming and refining the Big Bang theory. Its existence was first predicted in the mid-20th century, and its subsequent discovery in 1965 by Arno Penzias and Robert Wilson provided strong evidence supporting the Big Bang model. Since then, various missions have mapped the CMB with increasing precision, transforming our understanding of the cosmos. Looking ahead at the universe's future, current science suggests it will keep expanding forever. As it expands, it's expected to cool down gradually. Over time, this cooling might reach a point where it's too cold for life as we know it, an outcome sometimes called the Big Chill or Big Freeze. If something called dark energy keeps pushing the universe to expand, galaxies will drift further apart. Stars will still form for a very long time. Stars, powered by nuclear fusion, exhibit varied lifespans and behaviors depending on their mass. Their life cycle, from birth in dense interstellar clouds to their final stages, significantly impacts the cosmos. Young stellar objects evolve through protostar and pre-main sequence phases, influencing the formation of planets and other stars. Main sequence stars like the Sun eventually swell into red giants, with their cores collapsing to form white dwarfs. Massive stars undergo more dramatic ends, exploding as supernovae and leaving behind black holes or neutron stars. These processes enrich the interstellar medium and trigger the formation of new stars, playing a fundamental role in the cosmic cycle of matter and energy. Eventually, the materials needed to make new stars will run out, and the universe will slowly become darker as the stars burn out. Far in the future, if certain theories are right, only black holes might remain, but even they might fade away over time. In the very end, if everything in the universe evens out temperature-wise, there might be a point where nothing more can happen, leading to what's known as the universe's heat death. These insights into the formation and future of the universe not only deepen our understanding of the cosmos, but also highlight the ever-changing nature of our universe, from its fiery beginnings to a future marked by an expansive and cooling cosmos. Everything in the universe, from the littlest parts of atoms to the biggest groups of stars, is made by the small pieces of matter and the laws that control them. Gravity is perhaps the most familiar to us. It's what keeps our feet on the ground and the Earth in orbit around the Sun. Gravity can be understood as bends and curves in the fabric of space-time, an idea brought forward by Einstein's general theory of relativity. Every object with mass distorts space-time, leading to the gravitational attraction we observe. Though gravity is the weakest of the fundamental forces, it works across infinite distances, playing a crucial role in the formation of the universe's structure. The next law, or force, is electromagnetism. This force powers our homes, keeps electrons in orbit around atomic nuclei, and allows for the formation of chemical compounds. Electromagnetism involves electricity and magnetism, which are interlinked. A moving electric field produces a magnetic field and vice versa. Unlike gravity, which acts on mass, electromagnetism acts on charged objects. It can attract or repel depending on the charges involved, and works at an infinite range. A strong nuclear force is what holds together the building blocks of atoms. It always attracts and operates at two different size scales in atoms. At the level of an atomic nucleus, it holds together protons and neutrons. On an even smaller scale, it binds together the quarks that make up these particles. The strong force is the strongest of the fundamental forces, but its influence is limited to very small distances. Weak nuclear force, on the other hand, can change one type of quark into another, which is crucial in processes like the nuclear reactions powering the sun and radioactive decay. It works at a scale even smaller than the strong force, and, while stronger than gravity, is considerably weaker than the strong and electromagnetic forces. At the heart of matter are elementary particles. The standard model of particle physics describes these particles, including quarks, which make up protons and neutrons, and leptons, which include electrons. This model explains three of the four fundamental forces, except for gravity, and how force-carrying particles influence quarks and leptons. Lastly, dark matter and dark energy are the universe's greatest mysteries. Dark energy, a term coined after observations by the Hubble Space Telescope, is thought to be driving the accelerated expansion of the universe. It's a mysterious force or energy fluid that fills space and makes up about 68% of the universe. Dark matter, on the other hand, constitutes about 27% of the universe. It's not visible and doesn't emit or absorb light, making it difficult to detect. However, its presence is infrared from its gravitational effects on visible matters and the structure of the universe. Current theories suggest dark matter could be made up of exotic particles like axions or WIMPs, weakly interacting massive particles. Understanding these forces and particles provides us with a deeper appreciation of the universe's complexity and beauty. From the force that binds atoms to the mysterious dark energy accelerating cosmic expansion, each element plays a vital role in the cosmic ball we are a part of. Galaxy formation and evolution are pivotal in understanding the universe. This process begins in a homogeneous state following the Big Bang, leading to the heterogeneous universe we observe today, full of diverse galaxies. The simplest model that is widely accepted today suggests that galaxies accumulate mass through clustering and merging, shaping their form and structure. Galaxy evolution theories must align with observed galaxy types to be valid. One critical factor in galaxy formation is dark matter. Galaxies are believed to contain far more mass in dark matter than can be directly observed. This unseen mass is necessary to explain the formation and rotation patterns of galaxies. Galaxy formation begins with a disk shape known as a spiral galaxy, characterized by spiral arm structures. However, the exact process by which these disk-like distributions of stars develop from a cloud of matter is still not precisely predicted by current theories. Early theories, like the one proposed by Egan, Lynden-Bell, and Sandage in 1962, suggested that disk galaxies formed through the massive collapse of a large gas cloud. This model has evolved, and more recent theories include the clustering of dark matter halos in a bottom-up process. In this theory, matter starts in smaller clumps, merging to form galaxies, which are then drawn by gravity to form galaxy clusters. Elliptical galaxies, some of the largest known, have a different formation and evolution process. Their stars are in randomly oriented orbits, not contributing to galaxy flattening like in spiral galaxies. Elliptical galaxies often harbor supermassive black holes at their centers, with the black hole's mass correlating with the galaxy's mass. The evolution of elliptical galaxies includes two main stages: the growth of the supermassive black hole by accreting cooling gas, and then the black hole stabilizing and suppressing gas cooling. Supermassive black holes play a significant role in galaxy evolution. Every massive galaxy likely contains a supermassive black hole at its center. Recent studies have shown that galaxies and their black holes grow together, indicating a close relationship between the size of a galaxy and its supermassive black hole. This relationship is self-correcting. If a black hole is too large for its galaxy, it grows more slowly due to a lack of available gas. And if it's small, abundant gas allows it to grow faster, catching up to its host galaxy. Now that we know so much about the universe and its ways, let's learn about the interstellar and intergalactic medium, or IBM, which plays a crucial role in the structure and evolution of the universe. This hot, tenuous gas, containing matter ejected from galaxies, constitutes a significant part of the universe's ordinary matter. While its average density is exceedingly low, the IGM's temperature reaches millions of degrees, generating X-rays that help astronomers analyze its composition. The IGM, comprising primordial hydrogen and helium from the formation of the first galaxies, as well as heavier atoms from later stages, is essential in studying galaxy formation and interactions. Astronomical phenomena like supernova remnants illuminate these gases, providing insights into the IGM's origins and characteristics. Moving on, we have gravitational lensing, a consequence of Einstein's theory of general relativity, which illustrates how gravity bends light. Massive astronomical bodies like galaxies and galaxy clusters magnify the light from distant objects, enabling the observation of otherwise invisible galaxies. Gravitational lensing allows the study of these distant galaxies, mapping the distribution of galaxies on the largest scales, and detecting exoplanets via microlensing. This phenomenon has become an invaluable tool in modern astronomy for exploring early galaxies, mapping dark matter, and measuring the effects of dark energy on the universe's accelerated expansion. Continuing with gravitational lensing, another fascinating aspect of modern astronomy is the study of black holes. These enigmatic cosmic objects, regions of space where gravity is so strong that nothing, not even light, can escape, are key to understanding the extremes of physics. Black holes are believed to form from the remnants of massive stars after they explode as supernovae. The immense gravitational pull of black holes affects nearby stars and gas, often creating spectacularly bright objects known as quasars when they feed on surrounding material. The study of black holes not only sheds light on the evolution of galaxies, but also on the nature of gravity and space-time. The role of supernovae in the universe is another topic of great interest. These stellar explosions are among the most energetic events in the universe and are crucial for dispersing elements heavier than hydrogen and helium into space. This cosmic recycling process enriches the interstellar medium, providing the material for new stars and planets. Supernovae also play a role in regulating star formation in galaxies and contribute to the dynamics of galaxy evolution. The concept of exoplanets, planets outside our solar system, has revolutionized our understanding of the universe. The discovery of thousands of exoplanets has opened up new avenues for understanding planetary systems. These discoveries challenge our theories of planetary formation and habitability, and offer the exciting possibility of finding other Earth-like planets. The study of exoplanets involves various methods, including the transit method and radial velocity method, each contributing to our growing catalog of distant worlds. In addition to visible matter, the universe is filled with invisible components that play a crucial role in its structure and dynamics. One such component is dark matter, which, despite being invisible, exerts gravitational effects on visible matter, radiation, and the large-scale structure of the universe. The nature of dark matter remains one of the greatest mysteries in modern physics. Various theories propose that dark matter could be composed of undiscovered particles like WIMPs or axions. Experiments and observations aimed at detecting these particles are ongoing and are central to our understanding of the universe's composition. The concept of cosmic strings, hypothetical one-dimensional topological defects formed in the early universe, is another intriguing aspect of cosmology. These strings, if they exist, would be incredibly thin and yet immensely dense, exerting a powerful gravitational pull. They are thought to have formed during symmetry-breaking phase transitions in the early universe and could potentially offer insights into the unification of fundamental forces. In studying the universe, astronomers and physicists also focus on cosmic microwave background (CMB) anomalies. While the CMB is remarkably uniform, certain anomalies like the cold spot and other unusual features challenge our understanding of the universe's isotropy and homogeneity. Investigating these anomalies could reveal new physics or deepen our understanding of the early universe. Lastly, the study of cosmic rays, high-energy particles that travel through space at nearly the speed of light, provides valuable information about the conditions of outer space. Cosmic rays, originating from the Sun, distant stars, and even other galaxies, can provide clues about the processes occurring in these extreme environments. Studying cosmic rays helps us understand the fundamental processes of particle acceleration and propagation in the universe. In conclusion, the universe is a complex and ever-evolving entity, full of mysteries and wonders. From the complicated galaxies to the enigmatic nature of black holes and dark matter, each discovery brings us closer to understanding the grand scheme of the cosmos. As we continue to explore and decipher the universe's secrets, we not only gain insights into our origins and the nature of everything around us, but also fulfill our innate curiosity about the world beyond our planet. The stars are the streetlights of eternity. But these fundamental building blocks of the universe are more than just twinkling points of light in the night sky. They are huge balls of fire that hold themselves together with their own weight, serving as the furnaces that make the most basic elements that everything else is made of. Stars have a life story of their own, from their fiery birth in the dense regions of space known to when they die and become something else. Their lives are full of a range of phenomena that highlight the dynamic and ever-changing nature of the cosmos. A star begins its life in a stellar nursery, where clouds of gas and dust collapse under gravity to form a protostar. This early stage is marked by intense heat and turbulence as the protostar contracts and its core temperature rises. Once the core temperature reaches a critical threshold, nuclear fusion ignites, marking the birth of a star. The main sequence phase follows, where the star shines steadily by fusing hydrogen into helium, maintaining a delicate balance between the outward pressure of nuclear fusion and the inward pull of gravity. But the story does not end there. Depending on their mass, stars meet different fates. The smaller ones swell into red giants before casting off their outer layers and retiring as white dwarfs. The more massive stars undergo a more dramatic transformation, exploding as supernovae and leaving behind either a neutron star or a black hole. These end states not only signify the completion of a star's life cycle, but also contribute to the cosmic cycle of matter, seeding the universe with the heavy elements essential for the formation of new stars, planets, and eventually, life itself. What I have just told you is just the tip of the iceberg. The grand cycle shows a lot more interconnectedness of cosmic phenomena, with each star's life and death playing a crucial role in the broader narrative of the universe's evolution. Today, let's dive deep into the tiniest details of how the twinkles in the sky are formed. The journey of a star begins in the vast cold expanses of space within nebulae, the stellar nurseries where clouds of gas and dust reside. These nebulae, with their breathtaking swirls of color and light, are not just spectacles of cosmic beauty. They are the birthplaces of stars. The process kicks off when parts of these clouds start to collapse under their own gravity, initiating the birth of a star. This collapse can be triggered by external forces such as shockwaves from nearby supernovae or the gravitational tug from passing stars, creating ripples that compress parts of the nebula to the point where gravity overtakes the internal pressures resisting collapse. As the collapse continues, the material at the center of the cloud begins to heat up, marking the formation of a protostar. This phase is highlighted by a delicate balance of forces. As the protostar contracts, gravitational energy is converted into heat, raising the core's temperature. However, at this stage, the protostar is not yet hot enough for nuclear fusion, the process that powers stars, to begin. Instead, it shines through the release of gravitational energy, gradually shedding its cocoon of gas and dust as it contracts. The school's observatory explains that these stellar nurseries contain all the ingredients necessary for star formation: hydrogen, helium, and trace amounts of heavier elements. The gravity and pressure, the heat and cooling, all these set the stage for the next critical phase in a star's life. The transformation from a protostar to a fully fledged star starts when it reaches a critical temperature and density at the core. When the core temperature soars to about 10 million Kelvin, hydrogen atoms begin to fuse into helium, releasing immense amounts of energy. This process, known as nuclear fusion, marks the protostar's transition into the main sequence phase of its life, where it will spend most of its existence steadily converting hydrogen into helium and radiating energy into space. This initial stage of star formation, from the gathering of dust and gas in nebulae to the ignition of a protostar, is both a delicate and exciting process. It highlights the complexity and elegance of the universe's mechanisms for creating stars, the fundamental units that light up the cosmos, form the elements essential for life, and ultimately shape the structure of galaxies. Through the study of nebulae and protostars, astronomers gain valuable insights into the conditions necessary for star formation, offering clues about the past and future evolution of our universe. Following the formation of a protostar, the next crucial phase in the journey of stellar evolution is the T-Tauri phase. This phase represents a transitional period for young stars, where they shed their embryonic clouds and begin to shine on their own. Named after the prototype of its class, the T-Tauri star, this phase is characterized by rapid changes and variability in brightness. The T-Tauri phase occurs after the protostar has condensed sufficiently, but before nuclear fusion of hydrogen into helium. The process that powers most of a star's life has begun in its core. During this stage, the star is relatively cool and large, with a surface temperature lower than that of main sequence stars. Despite this, T-Tauri stars are luminous due to their large size and the release of gravitational energy as they continue to contract. One of the most distinctive features of T-Tauri stars is their strong stellar winds and outflows. These winds are powerful enough to blow away the remaining gas and dust cloud that enveloped the star during its formation, clearing the surrounding space and halting the growth of more material onto the star. Another main point of the T Tauri phase is the presence of protoplanetary disks. These disks of gas and dust surrounding the young stars are the sites where planets can form. The actions of the stellar winds and magnetic activity not only help in clearing the material, but also in shaping these disks, influencing the formation and architecture of future solar systems. The T Tauri phase plays an important role in stellar evolution, marking a star's transition from a contracting protostar to a stable main sequence star. It is during this phase that a star establishes the conditions under which it will enter the main sequence, affecting its stability, lifespan, and the possibility of planet formation around it. Understanding T Tauri stars thus provides invaluable insights into the processes of star and planet formation, shedding light on the early stages of solar system development. This phase, while temporary, sets the stage for the long, stable period of hydrogen fusion that defines the main sequence of a star's life, underscoring the interconnectedness of each stage in the life cycle of stars. After transitioning from the T Tauri phase, the stars enter the most stable and lengthy period of their lives, known as the main sequence. This phase is characterized by the process of nuclear fusion, where hydrogen atoms in the star's core are fused into helium, releasing vast amounts of energy. This energy not only powers the star, but also provides the pressure needed to counterbalance the gravitational forces pulling the star inward, maintaining its stability. Nuclear fusion in the core of a main sequence star is a delicate balance of forces. The immense gravitational pressure at the core enables the temperatures and densities necessary for hydrogen nuclei to overcome their mutual electrostatic repulsions and fuse together. This fusion process emits energy in the form of radiation, which travels outward through the star's layers, eventually reaching the surface and radiating into space as the light and heat we observe. The rate of fusion depends on the core's temperature, which is why the mass of the star plays a crucial role in determining its lifespan and characteristics in the main sequence. The lifespan of a star in the main sequence varies dramatically based on its mass. Massive stars have higher core temperatures, enabling them to fuse hydrogen at a much faster rate than their less massive counterparts. Consequently, despite their larger fuel reserves, massive stars spend significantly shorter periods on the main sequence, sometimes only a few million years. In contrast, smaller stars with lower core temperatures and slower fusion rates can remain in the main sequence for billions of years. Our Sun, a relatively average star, is expected to spend approximately 10 billion years in the main sequence phase of its life. The difference in the lifespan of main sequence stars is not just a matter of long life, but also affects the star's evolution and the processes that follow the main sequence phase. Massive stars quickly exhaust their hydrogen fuel and move on to fuse heavier elements until they meet their end in spectacular supernovae, leaving behind neutron stars or black holes. Smaller stars like the Sun transition into red giants as they exhaust their hydrogen, eventually shedding their outer layers to reveal a white dwarf. The main sequence phase, therefore, is not just a period of stability, but a crucial factor determining a star's evolutionary path. The processes that occur during this phase, particularly nuclear fusion, have profound implications for the star's future and the cosmic environment. The energy released by stars in the main sequence phase is essential for the existence of life on planets like Earth and contributes to the synthesis of heavier elements necessary for the formation of new stars and planets. Understanding the main sequence phase is fundamental to comprehending the life cycles of stars and the dynamics of the universe. As stars like our Sun exhaust the hydrogen fuel in their cores, they exit the main sequence and move on to the next stage of their stellar journey, entering the red giant phase. This phase is shown by the star expanding immensely as the outer layers absorb heat and swell, even as the core itself contracts. The expansion is due to the shell of hydrogen around the core igniting, causing the star's luminosity to increase significantly, even though its surface temperature decreases. This transformation into a red giant signifies a star's struggle to find a new equilibrium as it starts to fuse helium into heavier elements like carbon and oxygen in its core. Following the red giant phase, low to medium mass stars shed their outer layers, creating a beautifully colored shell of gas known as a planetary nebula. This process unveils the hot, dense core of the star, now called a white dwarf. This core is incredibly compact, with a mass similar to the Sun's but a volume comparable to Earth's. A white dwarf radiates its remaining heat into space, but no longer undergoes nuclear fusion, slowly cooling over billions of years. The final theoretical stage in the life of such a star is the black dwarf phase. However, the universe is not old enough for any white dwarfs to have cooled sufficiently to become black dwarfs. This stage represents the endpoint of stellar evolution for low to medium mass stars, where the star no longer emits significant heat or light, essentially becoming a cold, dark remnant of its former self. Each of these stages, from the red giant to the planetary nebula, and eventually to the white dwarf and the hypothetical black dwarf, illustrates the remarkable transformation stars undergo after their time in the main sequence. This sequence of events showcases the complex processes that govern stellar evolution, highlighting the delicate balance between the forces of gravity and nuclear fusion that stars navigate throughout their lifetimes. High-mass stars, significantly larger than our Sun, lead tumultuous lives that climax in spectacular cosmic events. These stars live fast and die young, spending millions of years as red supergiants before their dramatic end stages as supernovae, neutron stars, or black holes. The red supergiant phase marks a relatively brief period of stellar expansion, where the star swells to immense sizes, often hundreds of times larger than the Sun. When a massive star exhausts its nuclear fuel and its core collapses under the force of gravity, a supernova occurs. The outer layers of the star are blasted into space, releasing a tremendous amount of energy. This explosion not only illuminates the cosmos, outshining entire galaxies, but also seeds the universe with heavy elements essential for life and future star formation. The remnants of such explosions lead to the formation of either neutron stars or black holes, depending on the mass of the star's core post-supernova. Neutron stars are incredibly dense, with masses up to twice that of the Sun, compressed into a city-sized sphere. These objects spin at incredible speeds and can emit beams of electromagnetic radiation, observed as pulsars. Alternatively, if the core's mass exceeds a certain limit, gravity overwhelms all other forces, leading to the formation of a black hole, an object so dense that not even light can escape its gravitational pull. Imagine the universe and NASA science provide insights into these enigmatic end states, highlighting the significance of high-mass stars in the astrophysical context and their contribution to the dynamic evolution of the universe. The life cycle of high-mass stars, from their days as red supergiants to their ultimate fate, underscores the diversity and complexity of stellar evolution. Their journeys enrich the cosmic landscape, driving the processes that shape the universe. Other than supernovae marking the death of massive stars, supernovae also play an important role in the universe by creating and dispersing new elements across space. Different types of supernovae produce different elements depending on the mass and composition of the progenitor star. For example, Type 1a supernovae occur when a white dwarf star accretes enough mass from a companion star to trigger a thermonuclear explosion. This creates mostly iron and other elements up to nickel. On the other hand, Type 2 supernovae occur when a massive star runs out of nuclear fuel and collapses under its own gravity. This creates a shock wave that blasts the outer layers of the star, creating elements heavier than iron, such as gold, silver, and uranium. The chemical composition and diversity of the universe are influenced by the frequency and type of supernovae, as well as the initial conditions of the molecular clouds. Different regions of the universe may have different abundances of elements, depending on the history of star formation and supernova explosions. This may affect the likelihood and diversity of life in different parts of the universe, as different elements may be required for different forms of life. Some supernovae have been observed by humans throughout history, as they can be visible to the naked eye for weeks or months. One of the most famous examples is supernova 1054, which occurred in the year 1054 and created the Crab Nebula, a bright remnant that can still be seen today. Another example is supernova 1987A, which occurred in 1987 and was the closest supernova observed since the invention of the telescope. It was located in the Large Magellanic Cloud, a satellite galaxy of the Milky Way, and provided valuable insights into the physics of supernovae and their aftermath. The end states of stars, particularly supernovae, play a crucial role in cosmic recycling and the formation of new stars. Some stars end their lives as neutron stars, pulsars, or black holes, which are among the most extreme and fascinating objects in the universe. Neutron stars are the remnants of massive stars that collapse under their own gravity after a supernova explosion. They are incredibly dense, with a mass of about 1.4 times that of the Sun squeezed into a sphere of about 10 kilometers in diameter. They also have very strong magnetic fields and spin very fast, sometimes emitting beams of radiation from their poles. These are called pulsars, and they can be detected as regular pulses of light or radio waves. The first neutron star and pulsar were discovered by Jocelyn Bell Burnell and Anthony Hewish in 1967, earning them the Nobel Prize in Physics. Black holes are the ultimate end state of stars, as they are formed when the core of a very massive star collapses into a point of infinite density and zero volume, creating a region of space where nothing can escape, not even light. They are invisible to the naked eye, but they can be detected by their effects on the surrounding matter and light, such as gravitational lensing, accretion disks, and jets. The first image of a black hole was captured by the Event Horizon Telescope in 2019, showing the shadow of the black hole at the center of the galaxy M87. The death of stars is not only a spectacular event, but also a vital one for the evolution of the universe. The elements created and ejected by supernovae mix with the interstellar gas and dust, forming new molecular clouds that are the nurseries of new stars and planets. This process of cosmic recycling ensures that the universe is enriched with the diversity of elements that are essential for the formation of complex structures and life. From the birth of stars in the nebulae to their death in supernovae, neutron stars, or black holes, we have explored the fascinating and diverse stages of the life cycle of stars. The life cycle of stars is a remarkable example of how the universe is constantly changing, creating, and recycling matter and energy. Carl Sagan once wrote, "The nitrogen in our DNA, the calcium in our teeth, the iron in our blood, and the carbon in our apple pies were made in the interiors of collapsing stars. We are made of star stuff." By studying the life cycle of stars, we can learn more about our own place and role in the cosmic drama. I hope you learned something new today. Thank you for watching, and see you in the next video. Space is full of secrets that are stranger than fiction. More than just a collection of stars and planets, its tales are more mystifying than you could ever imagine. The stories are all the more amazing than science fiction because they're real. Today, we're flipping through some of these incredible cosmic tales, peering into the corners of the universe that leave even the experts scratching their heads in wonder. How about a planet where water is replaced by lava? That's right. Instead of water cycles, you've got rivers and oceans of flowing lava. It's called K2-141b, And it's as wild as it sounds. The surface is so hot that rock vaporizes and falls back down as stone rain. That's some crazy weather. Then there's the curious case of Fomalhaut b, a planet that turned out to be an illusion, a mirage made of dust from a colossal cosmic crash. It's like the universe played a game of hide-and-seek with us, and for a while, we totally fell for it. And there's the star that vanished without a trace. No supernova, no explosion, nothing. Just gone. A star in the Kinman Dwarf Galaxy did that. One day it was there, shining brightly, and the next day it was gone. It's like the universe pulled a magic trick on the grandest scale. Let's not forget about the star that survived its own supernova, a cosmic event that's supposed to be a star's dramatic final act. This star, however, shrugged off the explosion and kept on shining, albeit in a slightly different form. These are just some of the amazing stories that the universe has to offer. The universe always surprises us and makes us realize how much we still have to learn. There's always something new and unexpected waiting for us out there. Are you ready to be amazed? Let's get started. Diving into the secrets of our universe, let's explore the concept of Dyson spheres and alien megastructures, a topic that bridges the gap between science fiction and potential reality. Let's start with Dyson spheres and alien megastructures. A Dyson sphere is a hypothetical structure that would surround a star completely and capture most or all of its energy. It was named after physicist Freeman Dyson, who proposed the idea in 1960. He thought that an advanced civilization could use such a structure to meet its energy needs and that we could detect them by looking for stars that are dimmer than they should be. A civilization that could build a Dyson sphere would be classified as a Type II civilization on the Kardashev scale, which measures a civilization's technological advancement based on energy consumption. But are there any Dyson spheres out there? Astronomers have been looking for them, and they have found some interesting candidates. One of them is the Infrared Bright Galaxy, WISE J22 4436.12. This galaxy is very bright in the infrared spectrum, which means that it emits a lot of heat. Some scientists have suggested that this could be a sign of a galaxy-spanning civilization that uses Dyson spheres or similar megastructures around many stars. Of course, there are other natural explanations, like high rates of star formation, that could account for the brightness. But the idea of finding evidence of advanced alien life is exciting, and the search continues. Przybylski's star, or HD 101065, adds another layer of mystery to the cosmos with its peculiar chemical composition. Discovered by astronomer Antony Przybylski, this star is an anomaly due to the unusual abundance of certain heavy elements and rare earth metals in its spectrum. These elements are heavy and rare, and some of them are radioactive and decay very quickly. For example, the star has actinides like plutonium and neptunium, which are not normally found in stars. How did they get there? And how do they survive in the star's atmosphere for millions of years? There are many theories that try to explain Przybylski's star's oddities. One theory is that the star engulfed some planets rich with these heavy elements, and that they are still mixing with the star's outer layers. Another theory is that the star passed through a cloud of material that was enriched by a past neutron-star collision, which is known to produce heavy elements. And then there are some more speculative ideas, like the possibility of an advanced civilization that purposely seeded the star with these elements, maybe as a way of getting rid of their nuclear waste or as a way of sending a message to other civilizations. We don't know the true nature of Przybylski's star, but it shows us how the universe can surprise us and challenge our understanding. As we peel back the layers of these cosmic enigmas, we're reminded of the vastness of our ignorance in the face of the universe's complexities. The search for Dyson spheres and the study of stars like Przybylski's challenge our assumptions and push the boundaries of our cosmic understanding. What other peculiarities lie just beyond the reach of our current scientific grasp, waiting to be discovered? In our journey through the cosmos, we encounter phenomena that not only baffle our minds, but also challenge the very foundations of our understanding. Among these, the newfound blob and the great attractor stand as colossal landmarks in the cosmic landscape, each telling a story of the universe's complexity and magnificence. The newfound blob sounds like a simple term, but it is far from a simple thing. It is a colossal entity that is bigger than 200 million light-years, and it is one of the biggest things we have ever seen in the universe. It is made of gas and galaxies, and it helps us learn more about the universe and how it started. These things are also called Lyman alpha blobs scientifically. They are like bright lights that show us how galaxies and stars are made. The biggest one we have discovered is very far away, 11 billion light-years, and it shows us what the universe was like when it was only 2 billion years old. That was a period when the cosmos was in its formative stage of creating galaxies and stars. The study of such structures helps astronomers untie the mysteries of how matter assembled in the early universe, leading to the formation of the vast cosmic web that spans the observable cosmos today. Then there's the enigma of the Great Attractor, a gravitational glitch that pulls galaxies towards it at astonishing speeds. It is located near a group of galaxies called the Norma Cluster, which is about 220 million light-years away from us. This unseen force is so strong that it affects the movement of galaxies over hundreds of millions of light-years. The nature of the Great Attractor has long confused astronomers, as its gravitational pull suggests a mass that far exceeds what is observable in that region of space. This disagreement has led to theories that range from enormous concentrations of dark matter to the possibility of a supercluster of galaxies hidden behind the zone of avoidance, where dust and stars in the Milky Way's plane obscure our view. To find out what the Great Attractor is, we need to map out where the galaxies and matter are in the universe and how they are arranged. This will help us understand the shape of the universe and how dark matter affects it. These two things, the newfound blob and the Great Attractor, are very bizarre and important, but they are not the only ones. There are many other things in the universe that are also amazing and mysterious, like the Sloan Great Wall and the cold spot in the cosmic microwave background. These things are all part of the big picture of the universe, and they help us answer some questions about the universe, from the smallest things like quantum fluctuations to the biggest things like the observable universe. We learn more about these things by using our knowledge and technology, and by testing our ideas and theories about the universe. The study of structures like the newfound blob and the Great Attractor enriches our understanding of the cosmos, offering insights into the forces that shaped the universe and continue to drive its evolution. As we solve these mysteries, we inch closer to answering some of the most fundamental questions about the nature of the universe and our place within it. Among the cosmos's vast array of mysteries, the Sloan Great Wall of Galaxies and the Eridanus Supervoid stand as epic witnesses to the universe's grand scale and essential complexity. These colossal structures, each notable in their own right, challenge our fundamental understanding of the cosmic thread. The Sloan Great Wall, discovered through the Sloan Digital Sky Survey, is an immense structure composed of a filament of galaxies stretching over 1.38 billion light-years. This colossal wall of galaxies, situated approximately 1 billion light-years from Earth, presents a tough challenge to the cosmological principle, which suggests that the universe, on a large scale, should appear homogeneous and isotropic. The existence of such a vast structure raises profound questions about the very nature of the universe, suggesting complexities and scales that our current models struggle to accommodate. The Sloan Great Wall's sheer size implies that cosmic structures can exist on scales far beyond what was previously considered possible, hinting at the amazing diversity that makes up the universe's large-scale structure. In stark contrast to the densely packed galaxies of the Sloan Great Wall is the Eridanus supervoid, an immense region of space nearly devoid of all matter. Spanning about 1 billion light-years across, this supervoid represents one of the largest known voids in the universe. Its discovery has perplexed astronomers, as the void's size and emptiness rebel against current cosmological theories that cannot easily explain such a vast expanse of emptiness. Theories regarding the origin of the Eridanus supervoid range from fluctuations in the density of matter in the early universe to more speculative ideas, such as the impact of a parallel universe. The latter suggests that our universe may have collided with another, leaving behind a bruise in the form of the Eridanus supervoid. This hypothesis touches upon the empire of multiverse theory and the enigmatic nature of dark energy and dark matter, further complicating our quest to understand what else might be hiding in the dark. These two things, the Sloan Great Wall and the Eridanus supervoid, are very different, but they both push us into deeper inquiries about the universe's underlying principles. The Sloan Great Wall challenges the apparent uniformity of the cosmos, while the Eridanus supervoid invites us to consider the universe's vast emptiness and the forces that shape such voids. These structures, in their enormity and uniqueness, serve as inspirations, guiding us through the complexities of cosmic evolution, from the densest galaxy clusters to the most barren voids. The transition from discussing these vast structures and voids to exploring the enigmatic objects that inhabit these spaces is a journey from the macroscopic scales of the universe to the complex details of its constituents. Just as the Sloan Great Wall and the Eridanus supervoid reveal the grand image of the cosmos, the stars, planets, and other celestial bodies that dwell within and around these structures offer a closer look at the cosmic tale. Each galaxy within the Sloan Great Wall, each empty pocket within the Eridanus supervoid, tells a story of cosmic forces at play, from gravitational interactions to the mysteries of dark matter and dark energy, shaping the universe. In the cosmic arena, quasars stand out as some of the most luminous and energetic objects, acting as lights that illuminate the vastness of the universe. Quasars are among the brightest and most distant sources of electromagnetic radiation in the sky, emitting up to 1,000 times the energy output of the Milky Way. They are thought to be powered by supermassive black holes at the centers of distant galaxies, which can have masses of millions or billions of times that of the Sun. As matter falls into these black holes, it forms a hot spinning disk of gas and dust that radiates across the electromagnetic spectrum, from radio waves to gamma rays. Quasars also produce powerful jets of plasma that can extend for millions of light years, creating spectacular lobes of radio emission. Among the billions of quasars that populate the cosmos, some are found to cluster together in groups that span enormous distances. These are known as large quasar groups, LQGs, and they represent the largest astronomical structures in the observable universe. LQGs are indicators of the distribution and density of matter in the universe, as they trace the regions where matter is more concentrated and gravitationally collapsed. The discovery of LQGs, therefore, has important implications for our understanding of the origin and evolution of the universe, as well as the nature of the dark matter and dark energy that dominate its composition. One of the most remarkable LQGs ever discovered is the huge LQG, a colossal structure that contains 73 quasars and spans more than 1 billion light-years. The huge LQG was detected by a team of astronomers led by Roger Close from the University of Central Lancashire, using data from the Sloan Digital Sky Survey, a comprehensive survey of the sky that has mapped the positions and properties of millions of celestial objects. The huge LQG is located in the constellation of Leo, at a distance of about 9 billion light-years from Earth, meaning that we see it as it was when the universe was less than half of its current age. The huge LQG is not only remarkable for its size, but also for its challenge to the cosmological belief, a fundamental assumption in modern cosmology, that states that the universe is homogeneous and isotropic on large scales, meaning that it looks the same in all directions and locations. The cosmological principle supports many of the models and theories that describe the universe, such as the Big Bang Theory and the Lambda CDM model. However, the existence of the huge LQG, with its sheer size and concentration of quasars, suggests that the universe may be more lumpy and structured than previously thought. This discovery forces astronomers to re-evaluate the scales over which the universe becomes homogeneous and isotropic, pushing the boundaries of our cosmological models. Then there's the enigmatic phenomenon of Tabby's star and other so-called Dipper stars. Tabby's star, officially known as KIC 8462852, is a star in the constellation of Cygnus, about 1,500 light-years away from Earth. It is a main-sequence star, similar to the Sun in mass and temperature, but slightly larger and brighter. Tabby's star was observed by the Kepler Space Telescope, a mission that monitored the brightness of more than 150,000 stars in search of planets that transit in front of them, causing periodic dips in their light curves. However, Tabby's star exhibited irregular and significant dips in brightness, up to 22%, that lasted for days or weeks and did not follow any discernible pattern. This behavior defied easy explanation and sparked a burst of speculation and investigation among the scientific community and the public. Various hypotheses have been proposed to explain the star's unusual light fluctuations, but none to date fully explain all aspects of the curve. Some people think there might be a bunch of comets, dust, or rocks blocking the star's light. Others think there might be a big planet with rings and moons around it. Some even think there might be huge structures built by aliens, like giant solar panels or spheres. While the latter suggestion is more fiction, the ordinary explanations, such as the destruction of a planet or a cloud of debris, are considered more reasonable by the scientific community. The mystery of Tabby's star has sparked a renewed interest in stellar astronomy, leading to the discovery of more stars with similar behaviors, such as EPIC 204278916 and Triple VWIT07. These observations expand our understanding of the diverse phenomena that can occur in star systems, challenging our assumptions about the stability and predictability of stellar light output. This exploration of the cosmos, from the vast flocks of quasars in the LQG to the odd dimming of individual stars like Tabby's star, highlights the incredible diversity and scale of phenomena in the universe. Each discovery, each glitch, pushes the limits of size, from the largest structures spanning billions of light-years to the intricate details of star systems and the forces that shape them. So, as we turn our gaze back from the cosmos to our small blue planet, we carry with us a renewed sense of wonder and a reminder of our lasting quest for knowledge. As Stephen Hawking once said, "Look up at the stars and not down at your feet. Try to make sense of what you see and wonder about what makes the universe exist. Be curious." The universe, with all its mysteries and marvels, awaits, and our journey into the vast stretch of the cosmos is far from over. It's a journey that goes beyond the limits of our current understanding, inviting us to dream, to question, and to explore. In this grand adventure, we are not just observers, but participants in the unfolding story of the universe. So, let's keep looking up, questioning, and exploring. The universe is a grand puzzle, and we've only just begun to. Every light in the sky tells a billion-year-old story, waiting for us to listen. Think about it. Every star, every flicker, is not just a distant sun, but a powerhouse of energy and life-shaping forces. From the scorching surfaces of stars, bursting with energy enough to forge the atoms that make up our very existence, to the explosions of supernova that outshine entire galaxies, all of these showcase the extreme conditions where the laws of physics are pushed to their limits. Today, we will discuss some of the most powerful objects in the universe. With each object, we piece together the story of our universe, the shared history of every atom, planet, and living thing in the universe. Let's connect the dots between these celestial phenomena, each a powerful force with an impact that echoes through space and time. Black holes. The first item on our list is black holes. Black holes are one of the cosmos's most enigmatic and powerful phenomena, embodying extreme conditions of mass and gravity. These are not actual holes, but rather immense masses concentrated into very small areas of space, creating gravitational fields so intense that nothing, not even light, can escape from them once it crosses the event horizon, which is the boundary around the black hole. One of the most fascinating aspects of black holes is their ability to be detected indirectly. Despite their invisibility in the electromagnetic spectrum, black holes reveal their presence through their interaction with surrounding matter. Accretion disks, which are rings of gas and dust orbiting at high speed, emit light across various wavelengths as matter is pulled in. This process can release immense amounts of energy, making the regions around black holes some of the most luminous in the universe. The detection of these emissions, along with the observation of stars' orbits being affected by a black hole's gravity, allows scientists to study these cosmic giants. Gravitational lensing, where light from distant objects is bent around a black hole, and the detection of gravitational waves from massive objects accelerating through spacetime, provide additional methods for studying black holes. Among black holes, supermassive black holes, SMBHs, like TON 618, represent the extreme end of the scale in terms of mass and gravitational pull. The peculiar density of supermassive black holes, SMBHs, like TON 618, juxtaposed with their formidable mass and gravitational influence, underscores a fascinating aspect of these cosmic phenomena. This seemingly paradoxical nature, where an object of such colossal mass can have an average density lower than water within its event horizon, is a consequence of the way black holes warp the fabric of spacetime itself. The vastness of an SMBH's mass stretches the space around it to such an extent that the volume contained within its event horizon becomes incredibly large. As a result, despite the black hole's mass being millions to billions of times that of the Sun, its average density can appear surprisingly low when calculated by dividing its mass by the volume of space it encompasses. This calculation, however, doesn't diminish the black hole's gravitational pull near its event horizon, where the curvature of spacetime ensures that not even light can escape. The presence of an SMBH at the center of nearly every large galaxy suggests a deep intrinsic link between the growth of black holes and the galaxies that host them. This relationship is evident in the observed correlations between the mass of SMBHs and the properties of their host galaxies' bulges, pointing to coevolution processes that have yet to be fully unraveled. The history of supermassive black hole research is a journey of discovery that stretches back decades, with early observations of quasars leading to the realization that these incredibly bright objects were powered by massive compact objects, later understood to be SMBHs. Scientists like Martin Schmidt and Donald Lynden Bell played an important role in identifying the properties of quasars and the mechanics of matter accretion onto SMBHs, providing critical insights into their nature. The idea that matter falling onto a massive compact object could explain quasars' luminosity laid the groundwork for our current understanding of SMBHs. The concept of black holes challenges our understanding of physics, offering a glimpse into the extremes of gravity and mass. Their study, not only enriches our knowledge of the cosmos, but also pushes the boundaries of theoretical physics, offering insights into the very fabric of space-time. As research continues, our understanding of these cosmic behemoths evolves, revealing the dynamic and often surprising nature of the universe. Neutron stars and pulsars. Neutron stars represent one of the universe's most extraordinary phenomena, and they are born from the remnants of supernovae. These stars, in their final stages, burn through their nuclear fuel, leading to a catastrophic collapse under their own gravity. This collapse compresses their cores to such an extent that protons and electrons merge into neutrons, creating a neutron star. These stars are astonishingly dense, with masses about twice that of the Sun, but condensed into a sphere approximately 20 kilometers across, resulting in densities comparable to those of an atomic nucleus. Pulsars, a subtype of neutron stars, emit beams of electromagnetic radiation from their magnetic poles. These fields are aligned off-center from the neutron star's rotational axis. As the pulsar spins, these beams sweep through space like the beam of a lighthouse. When one of these beams crosses Earth, it appears as a pulse of radiation, ranging from radio waves to X-rays and gamma rays, depending on the pulsar. The first discovery of a pulsar in 1967 by Jocelyn Bell Bernal and Anthony Hewish marked a significant milestone, providing the first direct evidence of neutron stars' existence. The precision of pulsars is remarkable, with some rotating hundreds of times per second. This regularity allows them to serve as cosmic clocks, offering an unparalleled opportunity to test theories of gravity and the behavior of matter under extreme conditions. For example, the discovery of binary pulsars, where two neutron stars orbit each other, has provided critical tests of general relativity, particularly in the emission of gravitational waves predicted by Einstein's theory. The intense gravitational field of neutron stars leads to phenomena like the emission of gravitational waves and the potential for binary neutron star systems to merge, events that are of keen interest in the study of the universe's extreme conditions. The dense, rapidly spinning neutron stars offer clues about the state of matter at unimaginable densities, providing insights into nuclear physics and quantum mechanics in conditions that cannot be replicated on Earth. For instance, pulsars have become fundamental tools in the search for gravitational waves, the mapping of the galaxy's structure, and even in efforts to develop a galactic positioning system for future navigation in deep space. Over the years, the study of pulsars has evolved, with discoveries highlighting the diversity of neutron stars and expanding our understanding of their role in the cosmos. These include magnetars, characterized by their extremely strong magnetic fields, and millisecond pulsars, which spin hundreds of times per second due to the transfer of mass and angular momentum from a companion star in a binary system. The ongoing observation and study of pulsars not only enriches our knowledge of neutron stars, but also continues to challenge and refine our understanding of physics under the most extreme conditions found in the universe. Researchers utilize advanced observatories and theoretical models to explore the complex interactions within pulsars' magnetospheres, shedding light on the processes that drive their emissions and the evolution of their magnetic fields. Neutron stars and pulsars encapsulate the extraordinary complexities and extreme conditions of the cosmos, providing key insights into the laws of physics that govern our universe. Through continued research, they promise to unlock further secrets of the vast mysterious expanse that is our universe. Gamma ray bursts, GRBs. Gamma ray bursts, GRBs, are among the most violent and luminous events in the universe, showcasing the colossal energy and power hidden within the cosmos. These bursts, typically lasting from a few milliseconds to several minutes, emit more energy in a few seconds than the Sun will over its entire 10 billion-year lifetime. GRBs are classified into two main types: long-duration bursts, which are believed to result from the collapse of massive stars, and short-duration bursts, thought to originate from the merger of binary neutron stars, or a neutron star and a black hole. GRBs are divided into two primary categories based on their duration and, implicitly, their origins. Long-duration GRBs typically last more than 2 seconds and are associated with the collapse of massive stars. This collapse leads to the formation of a black hole, a neutron star, or possibly a magnet, releasing an enormous amount of energy in the process. The collapse also results in a supernova, a titanic explosion that outshines the entire galaxy in which it occurs. This process, known as the core collapse supernova, is thought to be responsible for the birth of long GRBs. The association between long GRBs and the death of massive stars has been solidified through observations of supernovae coinciding with GRB locations. Short-duration GRBs lasting less than 2 seconds are believed to result from the merger of binary neutron stars, or a neutron star, and a black hole. These cataclysmic events not only emit intense gamma radiation, but also produce gravitational waves and ripples in the fabric of space-time that were first directly detected in 2015. The merger of these compact objects leads to the formation of a kilonova, an event marked by the rapid production of heavy elements like gold and platinum. GRB 221009A, detected on October 9, 2022, stands out as an extraordinary phenomenon in the study of GRBs due to its unprecedented brightness and energy output. This event was so intense that it was 50 to 70 times brighter than any previous record holder, making it the most studied gamma-ray burst in history. The energy radiated by GRB 221009A was around 1.2 times 10 lambda 55 erg, placing it among the largest explosions known, alongside events like the MS 0735.6 plus 7421 event and the Ophiuchus supercluster eruption. The discovery of GRB 221009A not only challenged existing models, but also opened new avenues for understanding the extreme physics governing the universe. The burst's initial explosion was followed by a longer, slower emission across a broad electromagnetic spectrum, from radio waves to X-rays and extremely high-energy gamma rays. This afterglow phase is crucial for understanding the environment around the burst and the processes at play during and after the explosion. Comparisons with other GRBs show that GRB 221009A's fluence, the integrated flux over time and energy, was exceptionally high, making it significantly brighter at Earth than any previously observed burst. Its total energy emitted at the source and its peak luminosity also set new records, underscoring its rarity and significance in the study of cosmic phenomena. Studying GRB 221009A and similar events provides invaluable insights into the behavior of matter under extreme conditions, offering a glimpse into the processes that generate such high-energy photons. These observations help refine models of GRB emissions and contribute to our understanding of fundamental physics, potentially uncovering phenomena not predicted by current theories. In summary, GRB 221009A exemplifies the power and mystery of the universe's most extreme events. Its study not only advances our knowledge of gamma-ray bursts, but also enhances our understanding of the cosmos's vast energetic processes. Through continued observation and analysis, scientists hope to unravel more about these cosmic giants, shedding light on the universe's most explosive and energetic events. Quasars and active galactic nuclei. Quasars and active galactic nuclei, AGNs, are among the universe's most intriguing and powerful phenomena, illuminating the cosmos with the energy of billions of stars. These celestial objects represent the vibrant and dynamic nature of galaxies far beyond our own, acting as cosmic lighthouses that can be seen across vast stretches of space. At the heart of every large galaxy, including our Milky Way, lies a supermassive black hole, with a mass ranging from a few million to tens of billions of times that of our Sun. When material from nearby stars, gas clouds, or dust falls into the gravitational grip of these black holes, it forms an accretion disk. The friction within this disk heats up the material, causing it to glow across the electromagnetic spectrum, notably in visible, ultraviolet, and X-ray light. This glowing region around the supermassive black hole is known as an active galactic nucleus, AGN. Quasars represent the most luminous and energetic type of AGN, visible from billions of light-years away. They are characterized by their bright galactic centers, where the central supermassive black hole's immense gravitational force pulls in matter at such a rate that it emits vast amounts of energy. The journey to understanding AGNs began with the development of radio astronomy, which led to the discovery of distant radio sources such as Messier 87, Centaurus A, and Cygnus A. These observations paved the way for identifying quasi-stellar radio sources, or quasars, in the 1950s and 1960s. The redshift measurement of 3C273 by Martin Schmidt in 1963 was a pivotal moment, revealing quasars as extragalactic objects with luminosities far beyond any known galaxy. AGNs and quasars serve as tools for probing the distant universe, offering insights into the early stages of galaxy formation and evolution. They help astronomers study the extremes of energy and gravity, providing a glimpse into the processes occurring near supermassive black holes. Furthermore, observations of quasars like 3C273 have opened up new avenues for exploring cosmic history, allowing astronomers to observe conditions prevalent shortly after the Big Bang. With advancements in technology, telescopes like Hubble have observed various AGNs, capturing images of quasars billions of light-years away. These studies have enriched our understanding of how supermassive black holes interact with their host galaxies, influencing their evolution. Hubble's observations have revealed bright quasars in the early universe, providing insights into the conditions prevalent at that time. The study of AGNs and quasars continues to be a vibrant field of astrophysical research, encompassing both observational and theoretical aspects. It involves surveys to find AGN across a broad range of luminosities and redshifts, examination of the cosmic evolution and growth of black holes, and studies on the physics of black hole accretion and the emission of electromagnetic radiation from AGN. Quasars and AGNs are not just sources of immense power, but also keys to understanding the universe's most fundamental processes. They continue to challenge and inspire astronomers, offering a window into the dynamics of galaxies and the role of supermassive black holes in shaping the cosmos. Cosmic microwave background. Last but not least, we have cosmic microwave background on the list. The CMB stands as a monumental discovery in our understanding of the universe's origins and composition. It is essentially the afterglow of the Big Bang, the primordial explosion that marked the beginning of the universe 13.8 billion years ago. As the universe expanded and cooled from this incredibly hot and dense initial state, the energy released filled the cosmos with a sea of radiation that is now detected as the CMB. This radiation fills all space and is almost completely uniform, observed as a faint glow in the microwave portion of the electromagnetic spectrum. The discovery of the CMB in 1965 by Arno Penzias and Robert Wilson was pivotal, providing strong evidence for the Big Bang Theory and offering a snapshot of the universe when it was just 380,000 years old, a time when protons and electrons combined to form neutral atoms, making the universe transparent to photons for the first time. the CMB is not perfectly uniform. It contains tiny fluctuations that map the distribution of matter in the early universe. These minute differences in temperature indicate the initial seeds from which galaxies and large-scale structures eventually form. Understanding these fluctuations has been a key focus of cosmological research, shedding light on the universe's composition, including the proportions of dark matter and dark energy. Inflation, a rapid expansion of the universe that occurred a fraction of a second after the Big Bang, is thought to have stretched and smoothed out the universe, but also generated the slight irregularities observed in the CMB. This theory helps explain the uniformity of the CMB across vast regions of the sky that could not have been in causal contact with each other at the time of their emission. Research into the CMB has been propelled forward by numerous ground-based and space observatories, such as the Cosmic Background Explorer (COBE), the Wilkinson Microwave Anisotropy Probe (WMAP), and the Planck Space Observatory. These missions have refined our measurements of the CMB's anisotropies, providing deeper insights into the universe's early moments and the fundamental processes that have shaped its evolution. The study of the CMB polarization, a twisting of light that occurred due to the universe's expansion, offers potential insights into the very early universe, possibly revealing more about inflation and the behavior of the cosmos when it was a fraction of a second old. The BICEP, Background Imaging of Cosmic Extragalactic Polarization program, among others, aims to measure this polarization with high precision, hoping to unlock further secrets about the universe's infancy. The CMB is a cornerstone of modern cosmology, a radiation that not only confirms the Big Bang, but also serves as a tool for unraveling the universe's most fundamental mysteries. Its study represents a confluence of theoretical physics, astrophysics, and cutting-edge technology, with each discovery about the CMB pushing the boundaries of our knowledge about the cosmos. Each of these celestial phenomena offers a unique lens through which to view the story of our universe, a narrative sculpted by immense forces and ancient light. By studying these cosmic entities, we not only deepen our understanding of the universe's fundamental principles, but also connect with the grand continuum of space and time. As we continue to piece together this cosmic puzzle, we're reminded of the universe's complexity and the remarkable human pursuit of knowledge that drives us to explore the unknown. 71%. That's how much water exists on the Earth's surface. But could it be that in this entire universe, we are the only ones having this mix of hydrogen and oxygen? Or is there more? In our solar system, water is not just limited to Earth. It's a fascinating molecule that exists in various forms across our celestial neighborhood. On Mars, evidence of ancient rivers and lakes suggests that water once flowed on its surface. Moons like Europa and Enceladus have vast subsurface oceans beneath their icy exteriors, raising the possibility of hosting extraterrestrial life. Moving beyond our solar system, interstellar space is not a barren wasteland. It's filled with vast clouds of gas and dust where water molecules exist. These interstellar clouds are the birthplaces of stars and planets, and they contain the building blocks of water essential for cosmic formation. Moreover, the discovery of water vapor in the atmospheres of exoplanets has opened new avenues for understanding the prevalence of water in the universe. This finding hints at the potential for habitable worlds beyond our solar system and fuels our curiosity about the existence of life elsewhere. The presence of water in our solar system, interstellar space, and exoplanets underscores its cosmic significance. It's not just a vital ingredient for life on Earth. It's a fundamental component woven into the universe, shaping planetary bodies and influencing the prospects for extraterrestrial life. Water's presence across the cosmos suggests that it may play a crucial role in the formation and evolution of planetary systems. Our journey extends beyond planets to the moons of our solar system. For instance, Jupiter's moon Europa is believed to harbor a salty, subsurface ocean beneath its icy crust, potentially supporting life. Ganymede, another of Jupiter's moons, also has indications of a global underground saltwater ocean, possibly consisting of several layers of ice and water. Callisto, with its ice layer estimated to be about 124 miles thick, may have an ocean at least 6 miles deep directly beneath this ice. Saturn's moon, Enceladus, with its global ocean of liquid water beneath an icy shell, vents water into space from deep fissures near its south pole. Titan, Saturn's largest moon, is believed to have a salty subsurface ocean as well. The distribution of water in the solar system tells the story of planetary formation. The inner solar system was too hot for water to condense into liquid or ice on the planets, suggesting that water was delivered to these planets, possibly by comets and water-bearing asteroids. The study of Jupiter's water content is crucial to understanding the solar system's formation. Understanding the story of water in our solar system and beyond connects us to a larger part of the cosmos, suggesting that the water we use daily could have originated from celestial bodies like comets, ocean moons, or ancient seas on planets like Mars. Join us on this cosmic journey as we connect the vastness of space with the water in your glass. Tracing the red planet's watery past. Water, fundamental to life, is not confined to Earth within our solar system. Mars, our red neighbor, presents a history of water in its past, evident from dried riverbeds and polar ice caps. Mars' current arid state contrasts sharply with its potentially wet past, hinting at dramatic environmental changes. Venus, often considered Earth's twin, likely possessed substantial water in its early history. But now it's a dry, inhospitable world due to a runaway greenhouse effect. Looking beyond planets, the moons of gas giants hold fascinating water secrets. Europa, one of Jupiter's moons, is believed to harbor a vast subsurface ocean beneath its icy exterior. This ocean, warmed by tidal interactions with Jupiter, could provide conditions suitable for life. Saturn's moon. Enceladus intrigues scientists with its icy geysers, ejecting water vapor into space, suggesting an internal ocean. These findings on moons and planets paint a complex picture of water's role and distribution in our solar system, sparking curiosity about life's potential beyond Earth. Interstellar nurseries. Water's presence extends beyond our solar system into the vast reaches of interstellar space. In the cold, dark regions of the universe, water exists predominantly as ice on dust grains within dense molecular clouds. These clouds are the birthplaces of stars and planetary systems. As a star forms, the surrounding material, rich in water and other compounds, gradually coalesces to form planets, moons, and other celestial bodies. The role of water in these interstellar nurseries is vital. Water molecules participate in the complex chemistry of star formation, acting as a coolant that aids in the collapse of clouds into stellar and planetary bodies. The abundance of water in these regions can significantly influence the composition and formation processes of emerging planetary systems. Understanding water in interstellar space is crucial for comprehending the origins of water on planets like Earth. This knowledge also provides insights into the conditions necessary for life as we know it, guiding our search for habitable worlds in the universe. The quest for exoplanetary water. The discovery of water vapor in exoplanet atmospheres marks a significant milestone in our understanding of the universe. These exoplanets, located outside our solar system, often orbit stars in what is known as the habitable zone, where conditions might be right for liquid water to exist. Advancements in telescopic technology have allowed astronomers to detect the faint signatures of water vapor in the atmospheres of several exoplanets. This detection is crucial, as water is a key ingredient for life as we know it. The presence of water vapor suggests that these distant worlds could have conditions similar to Earth, potentially even supporting life. These findings are not just about the presence of water, but also about the diversity of planetary systems and their capacity to host life-sustaining environments. The study of water on exoplanets helps us understand the distribution of habitable worlds in the universe and challenges our perspectives on the uniqueness of Earth. It propels our search for extraterrestrial life, driving us to ask whether Earth is the only blue planet in the cosmos or just one among many. The process of water formation in the universe begins at a molecular level within the dense, cold molecular clouds scattered in interstellar space. These clouds, comprising hydrogen and oxygen, are fundamental to the birth of stars and planetary systems. When gravity pulls these clouds together, they collapse and form stars, kickstarting a series of reactions that lead to the formation of water. The intense heat from the forming star causes most of the hot water vapor to dissipate into space. However, cooler water molecules, in the form of liquid and ice, remain. These water molecules, primarily ice, envelop dust particles. As these icy dust grains accumulate, they serve as building blocks for the formation of planets and other celestial bodies in the emerging solar system. This process ensures that nascent planetary systems possess sufficient water, potentially creating environments conducive to life. Understanding the formation of water in these star-forming regions is crucial for comprehending the origins of water on planets, including Earth, and is a key element in the search for habitable exoplanets. Exploring our ocean worlds. Water is central to the search for extraterrestrial life due to its fundamental role in supporting life processes. All known life forms on Earth require liquid water to survive, making it a primary indicator of potential habitability in astrobiology. This understanding drives much of the exploration in our solar system and beyond. For instance, the search for evidence of water on Mars has been a significant focus, given the planet's similarity to Earth in terms of rotation period and axial tilt. Early observations suggested the presence of water or vegetation on Mars, but further studies revealed a much drier and colder environment, with minimal amounts of water vapor in its atmosphere. However, the discovery of geological features resembling dry riverbeds and the presence of clay minerals formed in fresh water on Mars have reignited interest in the planet's watery past and its potential to have supported life. The exploration of Mars, including missions like Mariner 9 and the Viking landers, has been crucial in shaping our understanding of water's role in supporting life on other planets. The celestial water bearers. Comets and asteroids have long been theorized to play a crucial role in delivering water to planets like Earth. These celestial bodies, rich in water and organic compounds, are remnants of the early solar system, providing a unique window into the past. Water molecules on Earth and other celestial bodies likely predate our Sun, originating in the vast clouds of gas and dust between stars. These molecules, once part of the protoplanetary disk, were incorporated into comets and asteroids. The water found on these space rocks closely matches the water composition on planets, particularly the ratio of hydrogen to deuterium, a hydrogen isotope. This composition suggests that water forms at cold temperatures on the surface of dust grains in these interstellar clouds. This process leads to a higher incorporation of deuterium in H2O molecules, aligning with the water composition found in comets and asteroids. This understanding challenges the hot nebular theory, which posits that water breaks down in the heat of a protoplanetary disk and reforms as things cool down. The discovery of water on comets and asteroids has significant implications for understanding how water, an essential ingredient for life, arrived on planets. The presence of water in the early universe sheds light on the conditions present during the formation of early planetary systems. Water molecules in space are primarily formed in dense molecular clouds, where they play a pivotal role in the development of new stars and planets. Research using observations from telescopes like the Herschel Space Observatory has provided insights into the movement and behavior of water molecules in these regions. In star-forming regions, water molecules, primarily in the form of ice, attach to dust particles. These particles then clump together, contributing to the development of planets and moons around newly formed stars. This research indicates that newly formed planetary systems are likely to have substantial amounts of water, essential for potentially habitable environments. The study of water in these early stages of star and planet formation is crucial for understanding the origins and distribution of water in the universe. It also helps us comprehend the conditions necessary for the emergence of life, guiding our search for habitable worlds beyond our solar system. The quest for Earth's twin in the stars, NASA's scientific exploration, subsurface access mechanism for Europa, Sesame, and concepts for ocean worlds life detection technology, cold tech programs have been focusing on the potential habitability of ocean worlds like Europa and Enceladus. These programs aim to develop technologies capable of penetrating the ice shells of these moons to access the subsurface oceans. Key components for such missions include nuclear power systems for melting through ice, thermal management systems, and robust communication links through the ice shells. Challenges such as navigating through impurities in the ice and ensuring reliable communication with the lander are being addressed. These explorations are significant because the subsurface oceans of these moons are considered potential habitats for extraterrestrial life. The composition and conditions of these oceans, hidden beneath thick layers of ice, hold the key to understanding the likelihood of life existing beyond Earth. Detecting water on exoplanets is another critical aspect of searching for life in the universe. Instruments designed to detect various wavelengths of light and particles like neutrons emanating from the surface of an extraterrestrial body can help identify atomic elements, such as hydrogen, a component of water. Landers and rovers can also collect samples from planetary surfaces to analyze their chemical composition, indicating the presence of minerals formed in liquid water environments. However, confirming the presence of water on extraterrestrial bodies is challenging due to the limitations of current technology and the complexities of space exploration. Sample return missions, while providing detailed analyses, are expensive and difficult to perform. Despite these challenges, the search for water on planets and moons continues to be a critical focus in the quest to find extraterrestrial life. The extremes of water in the cosmos. The exploration of water's behavior in the extreme environments of black holes and neutron stars is a subject that merges the worlds of astrophysics and chemistry. Neutron stars, remnants of supernova explosions, are among the densest objects in the universe, with gravity so intense that it crushes atoms together, forming a mass largely composed of neutrons. This extreme density alters the fundamental behavior of matter, including water, if it were present. The outer layers of a neutron star, composed of various elements like hydrogen, helium, and heavier ions, suggest that complex chemistry could occur in these high-pressure environments. Black holes, characterized by their intense gravitational fields, represent an even more extreme environment. Formed from the collapse of massive stars, their gravitational pull is so strong that not even light can escape. The behavior of matter, including water, near a black hole, especially as it approaches the event horizon, is a subject of significant scientific inquiry. The intense gravity and extreme conditions near black holes are likely to distort and stretch matter, leading to phenomena like spaghettification. While the presence of water in these extreme environments is still largely theoretical, the study of these cosmic phenomena provides invaluable insights into the behavior of matter under conditions that are impossible to replicate on Earth. Understanding how water and other substances behave near neutron stars and black holes not only broadens our knowledge of astrophysics, but also challenges our understanding of chemistry and physics in extreme conditions. Water plays a crucial role in shaping the climates of planets and moons across the universe, influencing a wide range of geological and atmospheric processes. On Earth, water is integral to the water cycle, involving evaporation, cloud formation, and precipitation, which sculpts landscapes through erosion and sedimentation. This cycle is not unique to Earth. Evidence suggests that similar processes involving water may occur on other celestial bodies, such as the Moon and Mars. Water's role in the evolution of celestial bodies. Planets like Venus and Mars offer striking examples of how water can influence planetary climates. Billions of years ago, Venus may have had oceans, but a runaway greenhouse effect boiled off this water, drastically altering its climate. Mars, once more, Earth-like, with a thick atmosphere and abundant water, has lost much of its water over time, transforming it into the cold, desert world we observe today. Ocean worlds in our solar system, like Jupiter's moons, Europa and Ganymede, and Saturn's moons, Enceladus and Titan, further demonstrate the diversity of water's role in extraterrestrial climates. Europa's subsurface ocean, maintained in a liquid state by tidal heating from Jupiter, and Enceladus's global ocean, beneath its icy shell, indicate the potential for habitable conditions far different from those on Earth. Titan, with its methane and ethane lakes and rivers, showcases how liquid hydrocarbons can play a role similar to water in shaping a moon's climate. Understanding water's role in planetary bodies is essential for unraveling the mysteries of our universe, including the evolution of protoplanetary disks, the water budget of terrestrial planets, and their habitability. As we continue to explore our solar system and beyond, water remains a key factor in our quest to discover life and understand the dynamic nature of other worlds. Water's influence on the formation and evolution of celestial bodies is profound and multifaceted. In the context of planetary formation, water plays a key role from the early stages in the protoplanetary disks, affecting the water budget of terrestrial planets and thereby influencing their geological activities and habitability. This is evident in the way water has shaped the solar system, from the formation of early solids to the processes of planetary and moon formation. The presence of water in various forms, ice, vapor in the atmosphere, and liquid oceans on different celestial bodies offers insights into the past and present conditions of these worlds. For instance, Earth's oceans have been a driving force in its geological and climatic history. Similarly, the loss of water on planets like Venus and Mars has significantly altered their climates and landscapes. Venus, lacking a strong magnetic field and experiencing a runaway greenhouse effect, lost its oceans, while Mars, once rich in water, now mostly harbors frozen water in its ice caps. Moons within our solar system, like Europa, Ganymede, and Enceladus, showcase how subsurface oceans and water ice can suggest the potential for life or unique geological processes. The exploration of these ocean worlds is crucial for understanding the role of water in celestial bodies and its implications for life and habitability in the universe. This exploration of water in the universe underscores its vital role, not just on Earth, but across our solar system and beyond. From ancient rivers on Mars and subsurface oceans on moons like Europa and Enceladus to the presence of water in interstellar clouds and on exoplanets, water is a fundamental cosmic element. It shapes landscapes, influences planetary climates, and is integral to the formation of celestial bodies. For humanity, this understanding deepens our connection with the cosmos, highlighting our shared origins and the universal nature of water. It raises profound questions about life's potential beyond Earth and our ongoing quest to explore the universe. Looking ahead, one can't help but wonder what secrets the future of space exploration will unveil about water's role in the cosmos. How will these discoveries shape our understanding of life and the universe we inhabit? Well, we will find our answers soon. But whatever impact it may have to humanity, I hope you learned something from this video. Thank you for watching.